We don't live in a typical part of the universe. Astronomers discovered that our entire galaxy, the Milky Way, sits inside a vast cosmic void, a region nearly 2 billion light-years wide, where matter is thinner and gravity is weaker than almost anywhere else in the cosmos. It isn't emptiness, but a gentle hollow in the dense fabric of the cosmic web, a place where the universe itself expands just a little faster than the cosmic average. Tonight, we'll explore the profound implications of what this emptiness does to light, to galaxies, and to our core models of dark energy, stepping through this quiet science calmly and clearly. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean a lot to me. Your support helps me keep improving these quiet science stories and reminds me that these stories still find their way to gentle hearts like yours. Now, let's start with the quiet puzzle. Are we really falling through a hole in space? What if Earth isn't sitting in the average expected part of the cosmos at all, but rather inside a hole so vast, so empty, that its sheer scale could subtly bend the very laws we use to measure reality? In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Len Cowie, quietly dropped a discovery that sent a soft tremor through modern cosmology. Their meticulously gathered data suggested that our entire Milky Way galaxy, along with its surrounding neighbors in the vast Laniakea supercluster, lies deeply embedded within a giant cosmic void. This enormous region is roughly 2 billion light-years across, a scale that is almost impossible for the human mind to grasp. And within this volume, the density of matter is an astonishing 20% lower than the cosmic average. This colossal, underpopulated region is called the KBC void, named from the initials of its discoverers. And if the existence and sheer size of this void are real, then the uniform universe we thought we observed might not look the same from anywhere else, making our perspective subtly unique. To understand how profoundly unsettling that possibility is, imagine this. All of cosmology, every map of galaxies, every estimate of the universe's age and expansion rate is built on a single, core philosophical assumption called the cosmological principle. It states that the universe, when viewed on a large enough scale, is uniform and isotropic, meaning it looks the same in every direction and is roughly the same everywhere you go. Einstein's equations, Hubble's law, and the standard model of cosmology all rely fundamentally on that elegant foundation of uniformity. But what if that foundation isn't true where we live? Keenan and his team analyzed the brightness and redshift of Type Ia supernovae, the crucial standard candles used to measure cosmic distances, along with detailed counts of galaxy densities, out to several billion light-years. They noticed something strange and consistent. Galaxies immediately near us appeared less clustered than the statistical models predicted. The farther they looked, the denser the space appeared to become, as if we were sitting uncomfortably near the center of a vast, underpopulated spherical region of the cosmic web. This wasn't just an observational glitch or a problem with a single telescope. It matched independent results gathered from massive previous surveys, including the 2-micron All-Sky Survey 2MASS and the Sloan Digital Sky Survey SDSS, all of which had already hinted that the local universe seemed unusually sparse and quiet. "It's not that we're special," Keenan suggested. "It's that our neighborhood may not be as average as we once thought." In the precise language of astrophysics, the numbers were clear and persistent. The mean density contrast, delta, I2, of the region surrounding the Milky Way was calculated to be roughly in $0.2, meaning we live in an area 20% less dense than the global cosmic mean. That is not a small difference in physics. In the finely tuned machinery of cosmological models, even a few percent variation in mass density can profoundly alter how light and gravity behave across billions of light years. If the immense volume of space around us contains significantly less matter, then the effect is immediate. Gravity here is slightly weaker. and weaker gravity means less resistance to the universe's expansion. This subtle difference could make it seem, from our unique perspective inside the void, that the entire universe is expanding faster than it really is globally. That idea leads directly into one of the biggest, most stubborn mysteries in physics today: the Hubble tension. This is the ongoing, profound disagreement between how fast the nearby universe appears to expand when measured locally using supernovae versus the slower rate calculated from the distant, ancient cosmic microwave background, CMB. Local measurements from supernovae and Cepheid variables near our region give a higher value, around 73 text-to-teams per megaparsec, but global observations from the CMB suggest a slower rate, closer to 67 of text by kilometers per megaparsec. Could our cosmic void be the elegant, simple reason for that difference? If the KBC void truly expands faster than the denser regions beyond it, any measurement of the Hubble constant made from inside it would naturally record a higher value. In other words, our cosmic address might be silently biasing our understanding of the universe's true age, its size, and even its ultimate fate. To visualize this, astronomers compare the large-scale structure of the cosmos to a sponge. The galaxies form long, interconnected filaments, the thin strands of matter, and the voids are the vast, empty bubbles between them. Roughly 90% of the entire cosmic volume is occupied by this quiet, empty space. We happen, by strange cosmic coincidence, to live in one of those bubbles, surrounded by denser walls of galaxies that are billions of light-years away. The edges of our KBC void are defined by immense, distant clusters such as Coma, Perseus, Pisces, and Shapley. Inside the void, the gravitational pull drops to a faint whisper, like a calm, still ocean after a storm. Light from distant galaxies must travel through this underdense region, subtly changing its energy, a measurable phenomenon known as the integrated Sachs-Wolf effect NASA's UMAP and ESA's Planck satellites both detected cooler spots in the cosmic microwave background that align with the positions of these large voids, possibly including our own. These cold patches are not errors. They are the fingerprints of emptiness written across the oldest light in the cosmos. This means our local environment is a natural laboratory for understanding dark energy. Inside the emptiness, where gravity loses its grip, dark energy becomes dominant, driving faster, unchecked growth of space itself. An observer living inside such a vast void could indeed measure an artificially high expansion rate. The emptier the region, the faster it appears to stretch. For now, we continue measuring light, mapping galaxies, and refining models that still, by necessity, depend on the assumption of uniformity. But if the KBC void's influence holds true, the next generation of telescopes, JWST, Euclid, Vera C. Rubin Observatory, might reveal that even the quietest, emptiest corners of space can silently rewrite the deepest equations of cosmology. Because sometimes it's not what fills the universe that changes everything. It's what's profoundly missing. And if the void we live in truly bends expansion, then the universe around us may not just be growing, it might be breaking its own rule of uniformity. That's where the next question begins. If space expands faster here than anywhere else, what happens to the trusted constants of physics themselves? The quiet revelation that Earth floats inside the vast KBC void, a region of low density and weaker gravity, immediately forces us to face a critical cosmic consequence. The void itself may be stretching space faster in our local neighborhood than anywhere else in the cosmos. This fundamental speed mismatch is known to astronomers as the Hubble tension, the stubborn, persistent disagreement between the two most reliable ways we have of measuring how quickly the universe expands. This tension is not a matter of slight rounding errors, but a profound 9% difference between measurements that are each precise to a few percent. When scientists observe distant, ancient relic light from the cosmic microwave background, CMB, using missions like ESA's Planck satellite. They calculate a slower global expansion rate, typically around $67 textual kilometers per megaparsec. But when other dedicated teams look closer, studying Cepheid variable stars and Type Ia supernovae within a few 100 million light-years of us, the number jumps significantly higher, settling near 73,000 textbashal kilometers per megaparsec. It may not sound like much to the casual listener, but in the finely tuned equations of cosmology, that difference is enormous. It suggests the universe could be hundreds of millions of years younger than current standard models predict, causing a genuine crisis in our understanding of cosmic history. For years, scientists have debated the cause of this discrepancy. Some have proposed entirely new particles, exotic physics operating in the early universe, or even an early burst of dark energy. But the simplest, most unsettling explanation whispers something much quieter. Maybe the space around us isn't average at all. If we truly reside inside a low-density region, a cosmic bubble where gravity is inherently weaker, then space here should stretch more freely, like a patch of elastic fabric that has been slightly loosened from its surrounding threads. In this view, the higher local expansion rate isn't an illusion caused by faulty equipment. It is a direct, measurable property of our specific cosmic neighborhood. To visualize this, we must slow down and picture the cosmic web again. The large-scale structure of the universe is built from long, vast filaments of galaxies that resist expansion, separated by immense, quiet bubbles, the voids. Within those voids, the overall gravitational pull drops because there is simply less mass to resist the pervasive outward push of dark energy. Matter outside these bubbles still pulls inward toward the dense filaments, but inside, the balance shifts dramatically. Here, dark energy dominates, effectively driving faster, unchecked growth of space itself. Ryan Keenan and his colleagues, who first mapped the KBC void, described this consequence with elegant simplicity. Our region may expand faster simply because there's less matter to hold it back. To test this, researchers turned to highly detailed computer simulations. Using powerful cosmological models like the Millennium Simulation, Illustris, and Eagle, cosmologists model precisely how underdense regions evolve over billions of years. They found that even modest voids, just a few 100 million light-years across, can increase the measured Hubble constant by several %. For a colossal supervoid like the KBC, nearly 2 billion light-years wide, the localized expansion effect could easily reach the full 900% discrepancy that is currently observed. NASA's Hubble Space Telescope and the new, powerful JWST have both played key roles here. Hubble refined the cosmic distance ladder using Cepheid stars and supernovae in nearby galaxies, while JWST is now observing fainter, more stable standard candles deeper into space. Yet both instruments measure light from inside our own cosmic neighborhood within the same potentially biased cosmic bubble. Imagine trying to precisely judge how flat the ocean is while standing unaware in the middle of a large, accelerating wave. That's the situation local cosmology faces. We're measuring the cosmos from inside a potential distortion of space-time itself. The deeper we look, the clearer the pattern becomes. Galaxies near us recede faster than expected, while those beyond the definitive edges of the KBC void, beyond roughly 300 megaparsecs, begin to match the slower expansion rate predicted by Planck's CMB data. The profound contrast between these two regimes, the fast local rate and the slow global rate, is what persistently fuels the Hubble tension. Astrophysicist Adam Rees, a Nobel laureate for discovering the universe's accelerated expansion, has publicly stated that the tension is not going away. If anything, it's getting worse as the precision of the measurements improves. Some theorists argue that the void explanation can't account for the entire difference, suggesting that it might only bridge part of the gap, with the local effect layered atop deeper, unknown physics occurring in the early cosmos. The truth may very well lie in both a real physical variation in our surroundings and some unknown energy shaping the early universe. ESA's upcoming Euclid mission aims to measure this phenomenon with extreme precision by mapping over 1 billion galaxies and constructing a full three-dimensional chart of cosmic density variations. If Euclid confirms a large-scale underdensity matching the KBC void, it would fundamentally reshape how cosmologists interpret every local Hubble constant ever measured from Earth. But there is a subtle, profound layer to this. In regions of low gravity like our void, time and light behave differently. Photons traveling through an underdense region experience less gravitational redshift, meaning they lose less energy as they climb out of the very shallow gravity wells. That subtly alters their apparent brightness and distance, both of which are crucial inputs for accurately measuring expansion. Even small systematic changes can ripple into large differences across billions of light-years. This is why cosmologists now cross-check every dataset, using tools like baryon acoustic oscillations, BAO, which are ancient sound waves frozen into the distribution of galaxies, acting as a cosmic yardstick. If expansion truly varies with environment, BAO patterns inside voids should appear stretched compared to those in dense regions. Meanwhile, simulations confirm that gravitational outflow, matter slowly drifting outward from void centers, can subtly influence the motion of nearby galaxies, pushing them apart faster than the pure Hubble flow predicts. Even our local group, including the Milky Way and Andromeda, may be caught in that subtle, accelerating outward drift. If true, this means the very fabric of space near us is under different physical conditions than the cosmic average, a gentle, persistent stretching invisible to the naked eye, but measurable across epochs, as Neil deGrasse Tyson once mused. We are participants in the great cosmic experiment, not spectators. The vast emptiness we drift through might be amplifying dark energy's outward push, quietly accelerating our corner of the universe faster than the rest. The deep implication is that every measurement we make of time, distance, and even the universe's age carries the fingerprint of this hidden bias. We are scientists measuring from inside a rapidly moving laboratory. But perhaps the most remarkable thing is how consistent the cosmos remains despite this local warp. Gravity, light, and motion still obey the same equations. It is only the overall scale that changes, like a quiet note resonating slightly higher than the rest, hinting at the profound, persistent presence of the void. The quiet revelation of the KBC void, our colossal, underdense cosmic address, doesn't just distort our local measurements of expansion, it leaves a subtle thermal signature across the very oldest light in the universe. This phenomenon provides tangible evidence that vast emptiness is not invisible but casts a profound gravitational shadow that we can detect. This shadow manifests as mysterious cold spots in the cosmic microwave background, serving as the void's fingerprints written across the ancient canvas of the sky. The cosmic microwave background, CMB, is the faint, pervasive radiation left behind from when the universe was only 380,000 years old. It's the most ancient light we can observe, a nearly perfect snapshot of the early cosmos, uniform in temperature to an astonishing degree. But as that light travels across the expanse of 13.8 billion years, passing through modern structures like galaxy clusters, thin filaments, and immense cosmic voids, it changes. It stretches, cools, or warms slightly, leaving behind subtle imprints that scientists can measure with incredible precision. Among these subtle fingerprints, the pattern of cold spots stands out. These are patches of sky that appear mysteriously colder than the cosmic average. When NASA's WMAP satellite first meticulously mapped the CMB in 2003, one of these cold spots shocked astronomers. It was unusually large, spanning nearly 5 degrees across the sky and significantly cooler by about 70 microkelvin than the theoretical expectation. For years, no one could definitively explain why this thermal anomaly existed. Then, the powerful ESA Planck mission confirmed the anomaly with even greater precision in 2015. Not only was the cold spot real, but it appeared to align perfectly with the position of a massive, known underdensity, the Eridanus supervoid, located about 3 billion light-years away. This alignment provided the first compelling evidence that cosmic voids can leave a measurable thermal imprint on the oldest light in the universe. To understand why this happens, we have to look at one of the most delicate effects in cosmology, the integrated Sachs-Wolf ISW effect. When a photon from the CMB passes through a dense region, it gains energy as it falls into the gravitational well and then loses the same amount of energy as it climbs back out, resulting in no net change. However, when a photon from the CMB passes through a region of low density, a void, it loses energy while climbing out of the shallow gravitational well. But because that region of space is expanding faster than average, the gravitational well effectively gets shallower while the photon is traveling through it. This subtle change means the photon doesn't regain all of its lost energy on the way out. The result, it exits slightly cooler than it entered. NASA describes it simply: light traveling through a growing void gets stretched and cooled by the universe's rapid expansion. In denser regions, the opposite happens, producing faint hotspots. But across the vast cosmic sky, these temperature shifts are minuscule, only a few millionths of a degree, barely perceptible, yet measurable with instruments like Planck's high-frequency instrument, which can detect temperature differences as small as 10 microkelvin. When researchers overlaid the Planck CMB maps with galaxy distribution data from the Sloan Digital Sky Survey, SDSS, the correlation became undeniable. Every significant cold spot corresponded to a known large-scale void, including the Boötes void, the Eridanus void, and even parts of the KBC void itself. This means that the emptiness around us isn't invisible. It leaves a measurable fingerprint on ancient light, and the thermal shadow of the KBC void where we reside is subtly woven into the CMB's delicate texture. Data analysis by Keenan, Barger, and Cowie in 2013 hinted at a faint, cold pattern extending across the region, matching the KBC boundaries. If confirmed, it would mean that the very photons from the Big Bang, the light that has traveled for 13.8 billion years, have been subtly altered by the void we live inside. It's one of those astonishing realizations in cosmology. The universe remembers where it is emptier. ESA's Planck team described it in technical terms. The temperature anisotropies are consistent with gravitational potential decay within underdense regions. In simpler words, voids act like cosmic coolers, chilling the background light as it passes through. The ISW effect is small but powerful. It gives astronomers a way to map the structure of gravity without seeing matter directly. By comparing maps of CMB temperature with large-scale galaxy surveys, scientists can trace where space-time is stretching faster or slower, revealing the hidden skeleton of the universe. That's why NASA calls the CMB the universe's baby picture with wrinkles that never go away. Those wrinkles aren't random. They are records of structure, the quantum seeds of galaxies and voids alike, magnified by cosmic history. Now, the James Webb Space Telescope, JWST, is adding a new layer to this investigation. By observing extremely faint, distant galaxies beyond redshift Zetas 10 Dollar, JWST provides anchor points for testing how these early structures evolved into today's cosmic web. The voids that now distort the CMB originated from tiny quantum ripples in the primordial plasma, ripples that were then amplified by dark energy over billions of years. The more recent finding is that by stacking data from thousands of known voids, researchers have detected a consistent pattern. Photons passing through voids are systematically cooler by about 9 microkelvin compared to random sky regions. It's one of the most subtle yet convincing signatures of large-scale structure we've ever observed. The CMB then isn't just a relic of the past, it's an active messenger of the present universe. Its light has been stretched, bent, and chilled by every structure it has ever crossed, a cosmic record of expansion, gravity, and time itself. The cold spots on that ancient sky truly mark the great hollows of space. This means our entire cosmic neighborhood, our galaxies, clusters, and even the local flow of time may all be defined by that subtle difference in temperature. Because in the end, the universe leaves clues everywhere, even in the warmth of its first light. And if the CMB reveals the fingerprints of our void, the next question is even more unsettling. How did these voids, these vast areas of quiet, concentrated nothingness, form in the first place? Could something as small as a quantum fluctuation be responsible for sculpting the cosmic desert around us? That's where we drift next, into the origins of structure itself. The quiet revelation that we are living inside the KBC void, a colossal, underdense pocket, forces us to step back and examine the universe's large-scale structure not as a random sprinkle of stars, but as a deliberate and precise pattern. Astronomers call this pattern the cosmic web, a grand architecture of matter and emptiness shaped by gravity over nearly 13.8 billion years. This structure is what gives rise to the idea of the sponge universe, where vast hollows define the presence of matter itself. Here is the staggering truth. If you could gather every atom in the observable universe, every star, planet, gas cloud, and galaxy, it would fill less than 1/billionth of the available space. The rest is emptiness, cold, vast, and mostly invisible. More than 90% of the universe's volume is made of voids, immense regions where the density of matter drops far below the cosmic average. These voids are not just accidental gaps between galaxies. They are the fundamental, defining feature of the universe's architecture. The galaxies, clusters, and filaments we see through powerful telescopes form the walls and threads, outlining this web like the delicate lattice of a sponge or the holes in Swiss cheese. Our Milky Way galaxy, our familiar cosmic home, sits along one of these thin filaments, a glowing thread of matter stretched across a nearly endless vacuum. From a cosmic perspective, we are an island floating in a dark ocean, surrounded not by more galaxies, but by deep, rapidly expanding nothingness. The story of how the universe came to look this way begins in its first fraction of a second after the Big Bang. The infant cosmos was almost perfectly smooth. Matter and radiation mixed evenly across space, uniform to an astonishing degree. But tiny quantum fluctuations, density differences as small as 1 part in $100,000, acted as the original seeds for all future structure. NASA's WMAP and ESA's Planck satellites mapped those ancient imprints in the cosmic microwave background, CMB. The bright and dark patches in their maps show precisely where matter was just slightly denser or thinner than average. $13.8 billion years ago, over billions of years, gravity relentlessly amplified those minuscule initial differences. Denser regions pulled in more matter, growing into massive clusters and long filaments. Conversely, the underdense regions, the future voids, expanded faster, pushing matter outward from their centers. The result is the structure we see today, a universe where most of the mass lies in narrow threads only a few megaparsecs wide, separating vast, quiet, empty spaces hundreds of megaparsecs across. The largest structures, such as the Sloan Great Wall, stretch over $1.4 billion light-years, yet remain just thin. Matter-rich membranes outlining the edges of enormous cosmic bubbles. The Bhuta's void, one of the emptiest regions known, spans nearly $330 million light-years and contains only a few dozen scattered galaxies. When astronomers plotted these structures using data from the Sloan Digital Sky Survey, SDSS, they saw a pattern that seemed almost organic, like a vast neural network glowing faintly in the dark. Each filament connects to others at dense nodes where galaxy clusters form, while the spaces between them stretch wider and quieter over time. This is not chaos. It is the predictable outcome of simple physics acting across unimaginable scales. Computer simulations, such as the illustrious TNG project Millennium and Eagle, reproduce this same intricate filament pattern by applying Einstein's general relativity to an expanding universe filled with dark matter and dark energy. Within those simulations, voids naturally emerge as the space is left behind when matter flows inexorably toward gravity's strongest wells. And yet, the more astronomers refine their models, the stranger this architecture appears. The voids, especially the largest ones, are often larger than expected, sometimes too smooth, almost too empty. The KBC void, the colossal structure we inhabit, is an extreme example, about 2 billion light-years across. In standard LCDM, lambda cold dark matter cosmology, such vast underdensities are incredibly rare, with estimated odds of less than 1 in a million. Still, observations confirm it. Surveys like 2MASS, DES, and Pantheon Plus supernova data all indicate that our local region contains significantly fewer galaxies per cubic megaparsec than the global average. The universe, it seems, is not evenly filled after all. The voids continue to expand faster than the walls around them. As dark energy stretches space, these bubbles inflate, merging into even larger cavities. Over cosmic time, galaxies drift toward the filaments, while the interiors of voids grow increasingly empty. If you could travel from the Milky Way outward through the local void, you'd pass through hundreds of millions of light-years of near-nothingness, with only a few faint dwarf galaxies scattered like dust. Instruments such as the JWST can now detect some of these faint systems, revealing how they evolve in extreme isolation. They form stars slowly, their gas pristine, untouched by the frequent violent collisions that occur in denser environments. In other words, voids are not dead zones. They are quiet zones. Their galaxies live in slow motion, aging gently as the rest of the universe races ahead. ESA's Euclid mission is now mapping these structures in detail. Its goal is to measure precisely how the shape and size of voids change over billions of years. Because if voids truly expand faster, they could reveal exactly how dark energy behaves, whether it's a uniform constant, as Einstein's cosmological constant suggests, or something dynamic, evolving with time. Voids, in this sense, are cosmic laboratories. By observing how light travels through them, scientists can test whether the geometry of space follows the strict predictions of general relativity, or if new physics is needed. The discovery that most of the cosmos is empty forced cosmologists to rethink what the term typical means. The average place in the universe isn't inside a galaxy or near a star. It's in the dark silence between them. That emptiness is the baseline, the true canvas of reality. Yet this isn't a flaw or a mistake. It's how gravity and dark energy coexist. Gravity collects matter into filaments, while dark energy drives the gaps wider apart. Together, they sculpt the sponge-like structure we see across the universe today. The emptiness, then, isn't absence. It's architecture. It gives structure, meaning defines where light travels, and sets the quiet rhythm of cosmic evolution. The walls of galaxies and the spaces between them are two halves of one dynamic system, constantly balancing the pull of gravity with the outward push of expansion. And in that balance, we exist, a single galaxy on a delicate thread drifting through a sea of accelerating silence. The quiet revelation that we reside inside the vast KBC void, a region of space nearly 2 billion light-years across, containing significantly less matter than the cosmic average, immediately introduces a profound philosophical and physical crisis into modern astrophysics. This crisis centers on the violation of the cosmological principle, the most sacred and fundamental rule upon which all of modern cosmology and much of Einstein's framework is built. This is the unsettling situation of being located at the improbable center, a place that statistically shouldn't exist but does, thereby challenging the cosmological principle itself. For more than a century, scientists have relied on a single, elegant assumption that on large enough scales, the universe is both homogeneous and isotropic, uniform in every direction and at every place. This is the cosmological principle, the quiet foundation of general relativity and every subsequent cosmological model, including the lambda cold dark matter, lambda CDM, standard model. Einstein introduced this principle in 1917 when he applied his general theory of relativity to the entire universe. He assumed that no observer could occupy a privileged position, allowing his equations to describe the cosmos as a smooth, self-consistent whole. The moment that assumption fails, the entire framework used to interpret cosmological data may be compromised. The discovery of the KBC void by Keenan, Barger, and Cowie in 2013 using data from the Sloan Digital Sky Survey, SDSS, 2MASS and Type Ia supernovae directly contradicts this essential uniformity. They found that the region surrounding the Milky Way, stretching nearly 2 billion light-years, contains about 20% less matter than the global cosmic average. Statistically, the odds of existing inside such an enormous underdense region are less than 1 in a million. And yet, all the evidence points to that being exactly where we are. If this underdensity is real and spans such an enormous scale, it means the universe is not perfectly uniform. The very assumption that our position is cosmically ordinary may not hold. The standard lambda CDM model assumes that when you average matter distribution over scales larger than about 300 million light-years, the universe smooths out. Clusters, filaments, and voids all statistically balance into a uniform sea of mass and energy. But the KBC void spans nearly 7 times larger than that smoothing scale, and its density contrast is far too deep to fit comfortably within lambda CDM predictions. In other words, our cosmic neighborhood looks statistically impossible, a colossal anomaly that defies the expectations of our current best model. NASA's WMAP and ESA's Planck satellites mapped the early universe with exquisite precision, confirming that the primordial fluctuations from the Big Bang were tiny, only 1 part in $100,000. Such small ripples, amplified by gravity over $13.8 billion years, should not have evolved into such an enormous modern void without violating the underlying assumptions of general relativity or the nature of dark energy. Yet here it is, a 2 billion light-year wide cavity right where we happen to exist. If this local underdensity affects local expansion, it could provide an elegant, natural explanation for why nearby galaxies recede faster, resolving the Hubble tension without requiring any exotic, new physics. But that simple explanation comes at a steep price. It fundamentally undermines the principle that our position is cosmically ordinary. If we find that the universe is not uniform on the largest scales, it doesn't just tweak a single parameter. It challenges the very geometry of space itself. As one ESA cosmologist put it, if we live in a void, we are forced to question the validity of the cosmological principle itself. The moment that core assumption fails, every equation calibrated to it, distances, ages, and expansion rates, may need recalibration. This leads to several possible explanations for the failure of uniformity. One possibility is that the distribution of dark matter is more irregular than models predict. Dark matter forms the scaffolding of the cosmic web, guiding normal matter into filaments and clusters. If dark matter clumps unevenly on ultra-large scales, then the universe could appear homogeneous only on scales far beyond what we can observe. Another possibility is cosmic variance, the statistical reality that because we can only observe one universe from one position, we may have simply drawn an unlucky sample. In this case, our region might be unusual but not unique, just one extremely random outcome in a vast cosmic lottery. However, simulations under standard lambda CDM conditions rarely produce voids as large and deep as the KBC. This statistical rarity has led some physicists to wonder whether the cosmological principle itself must be modified. Perhaps it is an approximation that breaks down under certain low-density conditions. If true, it would mean that cosmology, the science of the universe as a whole, cannot be perfectly described by a single global model. Instead, each vast region of space might follow slightly different expansion dynamics depending on local density and curvature. The upcoming Euclid mission and the Dark Energy Spectroscopic Instrument, DSI, are designed precisely to test this. By mapping billions of galaxies, they can check whether the large-scale structure remains statistically uniform beyond the KBC region. If they find persistent variations, that would signal the first observational breakdown of the cosmological principle. NASA's James Webb Space Telescope, JWST, adds another layer of data. By peering deep into the early universe, JWST observes galaxies forming less than 300 million years after the Big Bang. If the distribution of those ancient galaxies appears clumpier or more uneven than models predict, it would mean the seeds of our modern voids were planted from the very beginning. This realization that our cosmic address might not be typical leaves cosmologists deeply uneasy. The entire framework of observational cosmology depends on the assumption that Earth's view is not special. The moment that assumption fails, every number we infer about the universe, from its rate of expansion to its ultimate fate, could be an illusion of perspective. The universe is not a single smooth fabric. It may be a mosaic expanding unevenly, with vast empty patches like cosmic lungs breathing faster than the rest. And the KBC void might just be one of those lungs expanding quietly, distorting our measurements and challenging the belief that we occupy no special place in the cosmos. The future of cosmology depends on mapping this asymmetry, confirming whether we are indeed breaking Einstein's rule, a consequence that would force a fundamental rewrite of the universe's foundational laws. The great crisis facing modern cosmology, the Hubble tension, is not merely a mathematical disagreement. It is a profound stress test of Einstein's general relativity itself, specifically questioning its limits when applied to the uneven expanse of the cosmos. The tension pits the slower global expansion rate measured by the ancient cosmic microwave background, CMB, against the faster, local rate measured near the Milky Way. This discrepancy leads us directly to the consequence of living inside the KBC void, providing a powerful yet unsettling answer to the question: why local expansion runs ahead of the cosmic average if the KBC void is real, a vast region 20% less dense than the rest of the universe? Then general relativity predicts that the space within it must expand faster. This isn't a failure of the law of gravity. It's a consequence of its operation in an inhomogeneous environment. In regions of low density, the gravitational pull is inherently weaker, allowing the outward push of dark energy to dominate more effectively. Essentially, there is less mass, less gravity, and therefore less resistance to the accelerating expansion of space. Our void acts like a patch of fabric that has been loosened from its threads, allowing it to stretch more freely than the dense, tightly woven cosmic walls outside. This hypothesis has been rigorously tested using high-powered computer simulations, which enable cosmologists to evolve the universe over billions of virtual years. Projects like the Millennium Simulation, Illustris, and Eagle model precisely how underdense regions form and expand. These simulations confirm that even modest voids, just a few 100 million light-years across, can increase the measured Hubble constant by several percent. For a supervoid of the KBC's immense scale, nearly 2 billion light-years wide, the localized expansion effect could easily reach the full observed discrepancy of 5 toles and 10 aid per cent dollar, potentially resolving the Hubble tension entirely without invoking any exotic new physics. The impact of this localized acceleration is profound on our observational data. We are using Type Ia supernovae and Cepheid variable stars within our local neighborhood to calibrate the cosmic distance scale. But all these standard candles are being observed from inside the KBC void. If the space surrounding us is stretching faster, every galaxy we measure within that bubble will appear to be moving away from us quicker than a galaxy located in a denser, average region of the universe. This makes our local measurement of Qasim 73 text, kilometers per megaparsec, artificially high, a bias dictated by our cosmic address. The faster rate isn't an illusion caused by equipment error, but a very real property of our cosmic neighborhood. The difference between the two expansion regimes, the fast local rate and the slower global rate, is what relentlessly fuels the Hubble tension. Galaxies near us recede faster than expected, while those beyond the edges of the KBC void, roughly 300 megaparsecs away, slow down, aligning with the slower rate predicted by Planck's CMB data. This contrast between two regions of the universe, one moving ahead of the curve and one following the global average, is the observable fingerprint of the void. Furthermore, living inside a low-gravity region subtly changes the behavior of light and time. Photons traveling through our underdense void experience less gravitational redshift, meaning they lose less energy as they traverse the shallow gravitational well. This subtly alters their apparent brightness and, crucially, their calculated distance. This systematic change, combined with the faster expansion of the local space, means that every measurement we make of time, distance, and the entire cosmic timeline carries the indelible imprint of this hidden bias. The universe we see is not the statistically average universe. It is a localized, warped version defined by our position. To address this, cosmologists are not only running simulations, but using independent probes like baryon acoustic oscillations, BAO. These ancient sound waves frozen into the large-scale distribution of galaxies act as an unchangeable cosmic yardstick. If expansion truly varies with environment, the BAO patterns inside our void should appear stretched compared to those in dense regions, confirming the effect of the localized acceleration. The next generation of missions, including the James Webb Space Telescope, JWST, Euclid, and the Vera C. Rubin Observatory, are vital to this investigation. JWST is observing the faintest, earliest galaxies, while Euclid will meticulously chart the three-dimensional cosmic density variations. These instruments will test whether the acceleration rate returns to the global average beyond our void's boundaries. If the expansion rate slows definitively outside the KBC's edges, that would be the decisive proof that our void is real and locally inflating, demonstrating a clear limit to the assumption of cosmic uniformity. This doesn't mean Einstein's physics is broken. It means our application of it must be contextualized. General relativity remains sound, but its outcome depends entirely on the input, the local density, curvature, and gravitational potential. In the void, that density is low, allowing relativity's limits to be reached, where the outward push of dark energy accelerates unchecked. This humbling reality forces cosmologists to abandon the comfort of the cosmological principle and accept that our perspective is uniquely local. We are scientists measuring from inside a moving laboratory, where the very emptiness we drift through is stretching space faster than anywhere else. It is the void that quietly dictates why our local expansion runs ahead of the rest of the cosmos. The quiet revelation that we reside inside the vast KBC void forces us to ask a profoundly counterintuitive question. How can gravity push outward instead of pulling inward? It sounds impossible. Gravity, by every textbook definition, is an attractive force, the quiet architect that binds planets to stars, stars to galaxies, and anchors planetary systems. Yet in the vast, underdense regions of space known as cosmic voids, astronomers are observing something that appears to behave in precisely the opposite manner. Inside these voids, galaxies are not drawn inward toward a dense center. Instead, they drift outward, slowly but steadily, as though being repelled or pushed away by the very space around them. This subtle, pervasive phenomenon is called gravitational outflow, and it is one of the strangest yet most predictable consequences of living in a universe made mostly of nothing. To understand this apparent reversal of the gravitational force, we need to remember that gravity acts on differences in mass and the overall geometry of spacetime. In regions where matter is abundant, such as immense galaxy clusters, gravity acts as we expect, pulling everything inward toward the highest density point. But inside a void, the entire situation flips. The matter density outside the void in the surrounding filaments and walls is significantly denser than the interior. Therefore, the net gravitational force on any object within the void points outward toward the higher density walls of galaxies. It's not that gravity changes its fundamental nature, it's that the geometry of mass distribution reverses its direction of influence. As cosmologist Daniel Pomerade from CEA Paris explains, voids are not places where gravity disappears. They are places where gravity acts from the outside in. This outward motion is not just theoretical, it has been mapped and measured. In 2021, Pomerade and R. Brent Tully published a detailed three-dimensional map of our local universe, which vividly revealed how nearby galaxies move relative to the surrounding cosmic structure. Their study, utilizing data from the Cosmic Flows 3 catalog, showed that galaxies near the edge of the KBC void are receding faster than the cosmic average, clear evidence of this outward gravitational motion. Each void behaves like an expanding bubble embedded in space foam. The denser filaments surrounding it act as a gravitational shell, pulling matter outward from the low-density center toward the higher-density walls. Over billions of years, this creates an outflow velocity field where every galaxy inside a void moves away from its center at speeds reaching several hundred kilometers per second. The European Space Agency's ESA Euclid mission and the Dark Energy Survey, DES, both confirm this dynamic pattern through statistical analysis of galaxy redshifts. When plotted across vast volumes of sky, the motion lines diverge from the void centers and converge at the dense filaments, forming a complex flow structure that mirrors the web-like skeleton of the universe itself. NASA describes this cosmic motion as a delicate dance between attraction and expansion. In dense regions, attraction dominates, pulling matter inward. In the voids, dark energy and the relative gravitational pull of surrounding matter dominate, pushing matter outward. At first glance, this seems contradictory. Gravity cannot push. But what happens in a void is a matter of profound balance. The gravitational potential inside is shallower than outside, creating a gentle gradient or slope in space-time that causes matter to drift outward, away from the center. Computer simulations like Illustri's TNG and Eagle reproduce this perfectly. When the simulations are evolved over billions of years, regions that start slightly underdense naturally expand faster than average. Their interiors are thin and form measurable gravitational runoff zones. In the observational data, galaxies inside these voids move outward at speeds of $200 text to $400 text kilometers relative to the cosmic rest frame. This flow doesn't violate Einstein's theory. In fact, it's a profound prediction of it. In the equations of general relativity, expansion is governed by both density and curvature. A low-density region expands faster because there is less mass and gravity to slow it down over time. This leads to the strange impression that gravity itself has turned repulsive. But it's not gravity pushing outward in a fundamental sense. It's space itself expanding faster inside the void. As ESA's Planck mission put it, the emptier the space, the faster it grows. Observationally, the signature of this outflow is clear in galaxy velocity fields. The Bootes void, spanning about $330 million light-years, shows galaxies near its edges moving outward at roughly 230 dons text. Klipitias colors relative to the void's center. The same trend appears in the colossal Eridanus supervoid and the vast underdensity around our local group of galaxies. NASA's Cosmic Flows project tracks these motions using precise distance measurements, revealing these peculiar velocities, tiny deviations from the pure Hubble flow. The pattern is unmistakable. Galaxies flow outward from the centers of voids toward their surrounding walls. This phenomenon also directly affects the Hubble constant measured from inside a void. Because galaxies are receding faster relative to the observer, local expansion rates appear artificially higher than the cosmic average, further contributing to the ongoing Hubble tension. ESA cosmologist Thomas Bucket notes that the large-scale structure of the universe is a set of expanding voids separated by contracting filaments. This contrast, expansion inside, compression outside, defines the dynamic equilibrium of the cosmos. Voids, therefore, aren't passive gaps. They are engines of structure formation. By expanding faster than their surroundings, they stretch the filaments, feed galaxy clustering at their boundaries, and amplify the contrast between matter and emptiness. Even the CMB carries evidence of this. Photons passing through an expanding void lose energy, arriving slightly cooler than average. This subtle integrated Sachs-Wolf ISW effect produces the cold spots seen in Planck's all-sky maps, confirming the link between gravitational outflow and the universe's large-scale structure. In other words, the emptiness between galaxies is not static. It's active, expanding and reshaping the cosmic web, with its gravity behaving differently, not breaking, but adapting to a changing landscape of matter and energy. The scale of this effect is immense. Our home, the Laniakea supercluster, appears to drift toward denser regions near the Shapley concentration, while simultaneously being pushed from behind by the underdensity of our local void. As R. Brent Tully explains, we are falling toward Shapley, but we're also being repelled by the local void. Two cosmic forces, one pull, one push, define our motion through space. So inside the void, gravity can indeed appear to push outward. It's the natural outcome of asymmetry in density, the cosmic version of a gentle hilltop where everything rolls away from the center. Every galaxy inside such a region is drifting toward the surrounding walls, carried by the expansion of the void itself. It's a quiet realization that the universe is not uniform and that gravity's empire is shrinking, one void at a time. The universe breathes, collapsing where gravity is strong and expanding where it is weak. In that cosmic breath, the voids exhale, defining the very rhythm of the cosmos. The quiet revelation that immense, underdense regions like the KBC void exist at all brings us to a profound, almost philosophical question that strikes at the heart of our cosmic understanding. Does gravity break inside the void? What if there are vast, silent places in the universe where gravity, the same force that sculpts stars, binds galaxies, and anchors planetary systems, simply gives up its power to dominate? In these immense cavities, stretching for hundreds of millions, even billions of light-years, another force rises quietly in its place. The simple answer is that gravity does not break in the sense of vanishing entirely, but its influence is so profoundly altered that the equations governing its dominance shift entirely. In the vast emptiness between galaxy clusters, there exist regions so underpopulated that gravity loses its power to hold structures together, giving way to the pervasive outward push of dark energy. NASA's WMAP and Planck missions have established that dark energy makes up about 68% of the universe, while all normal matter, stars, gas, dust, and planets combined, accounts for less than 5%. Yet dark energy's influence isn't evenly felt everywhere. In the densest regions, gravity still fights back relentlessly, pulling matter inward and resisting expansion. But inside the voids, these vast hollows of near-nothingness, gravity significantly weakens, and the expansive force of dark energy pushes outward unchecked. As ESA cosmologist Thomas Bucket once remarked, in the cosmic voids, expansion is faster because gravity has no one left to talk to. It is a hauntingly simple truth. Where there is less matter, there is inherently less gravitational pull, and so space stretches more freely and efficiently. To observe this fundamental shift, astronomers map galaxies across enormous volumes of the sky, using large-scale surveys like the Sloan Digital Sky Survey, SDSS, the Dark Energy Survey, DES, and the new Euclid mission. When plotted in 3 dimensions, the universe clearly looks like a sponge. Filaments of galaxies form the dense, structural walls, while between them lie immense cosmic bubbles or voids. The voids aren't truly empty. They still contain faint wisps of hydrogen, a few scattered dwarf galaxies and invisible dark matter halos, but their average density is often only about 20% of the cosmic mean. That low density is enough for the equations of general relativity to start bending in unusual ways. In Einstein's framework, the curvature of spacetime depends directly on the total energy density. A lower density means less curvature, resulting in a flatter local geometry. But when dark energy is added to the equations represented by the cosmological constant sc lambda, that flat, underdense space begins to accelerate outward. Inside a void where matter is scarce, sc lambda double wins. This dominance of dark energy within emptiness is one reason cosmologists utilize voids as natural laboratories. By studying how light from distant galaxies travels through them, researchers can test whether dark energy truly acts as a uniform constant or if its strength changes with the low-density environment. NASA's Dark Energy Survey, using the Blanco 4-meter telescope in Chile, has mapped hundreds of such voids and measured how background galaxies are distorted by the weak gravitational lensing of foreground structures. The result was striking. Galaxies behind voids appear slightly larger and brighter than expected because the space between them has stretched more than usual. This phenomenon, consistent with gravitational outflow, matter being slowly pushed outward from void centers, shows that voids aren't static holes. They expand faster than the cosmic average, slowly inflating and growing as the rest of the universe expands. The physics inside them borders on aliens compared to a dense cluster. Because gravitational potentials are so shallow in the void, time dilation is weaker, meaning clocks inside voids tick slightly faster than those located in dense clusters. Temperature fluctuations in the cosmic microwave background, CMB, confirm this. Light passing through large voids cools by a few millionths of a Kelvin, an imprint known as the integrated Sachs-Wolf (ISW) effect. Planck's satellite maps showed one such region, the Eridanus supervoid, coinciding with a cold spot in the CMB, consistent with photons losing energy as they escape a rapidly expanding void. So, while gravity does not literally vanish inside these regions, it is profoundly altered. The equations of general relativity still apply, yet their fundamental balance shifts. Where the density drops below a critical threshold, gravitational attraction simply becomes too weak to effectively counteract the powerful outward push of dark energy. This competition defines the modern universe. On scales smaller than a few megaparsecs, gravity rules, binding galaxies and forming stars. On scales larger than about 100 megaparsecs, dark energy dominates, causing space itself to accelerate outward. In between, inside the vast cosmic voids, lies a fragile equilibrium, a cosmic truce where gravity is overpowered. Researchers at the University of Geneva modeled this transition and found that void interiors can expand up to $20 faster than dense filaments. That means any observer inside such a void like us would naturally measure a higher Hubble constant than an observer located in a dense galaxy cluster. This local acceleration doesn't tear atoms apart or disrupt local planetary orbits, but over billions of years, it relentlessly reshapes the cosmic landscape. Walls of galaxies thicken while the interiors grow emptier, slowly dividing the universe into a vast honeycomb of structures. The cosmic web is not static. It's a dynamic boundary between the reigns of gravity and dark energy. The James Webb Space Telescope's JWST deep field images have already begun to glimpse galaxies inside voids, small, isolated systems with fewer stars and less dust. They evolve more slowly, largely untouched by the frequent violent collisions that occur in denser environments. Studying these quiet galaxies tells us how matter behaves in regions where gravity barely whispers. Their chemistry is simpler, their rotation is calm, and their halos are faint. Yet, their very existence proves that even in near emptiness, gravity still sculpts structure, just more delicately and patiently. The largest voids, like the KBC void, show us the edge of gravity's reach. Inside our vast bubble, the rules of gravity are already changing. Space expands faster, time drifts slightly quicker, and light crosses distances just a little too easily. Every observation we make carries the fingerprint of that imbalance. It is a quiet reminder that the universe is not uniform and that gravity's empire is shrinking. One accelerating void at a time, the very existence of the KBC void, a monumental 2 billion light-year wide cavity in which our entire local supercluster resides, forces us into a profound, existential confrontation with the bedrock of our cosmic understanding. This immense, underdense region poses the startling, unsettling question: is our physics wrong? This concern arises because the void suggests a profound lack of uniformity in the universe, an asymmetric cosmos that violates the most sacred rule of cosmology, the one that built the modern universe, the cosmological principle. For more than a century, scientists have relied on the elegant, simplifying assumption that, when averaged over large enough scales, the universe is both homogeneous and isotropic, meaning it looks roughly the same in every direction and is roughly the same everywhere you go. This assumption, known as the cosmological principle, allowed Albert Einstein to apply his general theory of relativity to the entire cosmos, enabling his equations to describe the universe as a smooth, self-consistent whole. Every cosmological model since, from the Big Bang theory to the current standard, the lambda CDM model, has relied fundamentally on this principle. The moment evidence suggests this principle is violated, the integrity of our cosmic framework is instantly called into question. The discovery of the KBC void, with its approximately 20% lower than average matter density, directly challenges this essential uniformity. Statistically, the odds of us existing inside such a colossal, deep underdensity are less than 1 in a million. Yet all the observational data points precisely to this being our cosmic address. The standard, the lambda CDM model, assumes that matter distribution smooths out beyond scales of about $300 million light-years. The KBC void spans nearly 7 times that size, and its depth is far too profound to fit comfortably within the predictions of a globally uniform universe. Our cosmic neighborhood looks, statistically speaking, impossible. NASA's WMAP and ESA's Planck satellites mapped the early universe with exquisite precision, confirming that the primordial density fluctuations left by the Big Bang were tiny, only 1 part in $100,000. Such small, random ripples, amplified by gravity over $13.8 billion years, should not have evolved into such an enormous modern void without fundamentally violating the underlying assumptions of general relativity or the nature of dark energy. Yet here it is. If the KBC void is real, and its influence is as significant as the data suggests, it means the universe is not uniform on the largest scales, and the very assumption that our position is cosmically ordinary must be abandoned. If this underdensity is true and significant, it offers an elegant, internal explanation for the Hubble tension the stubborn disagreement between the slower global expansion rate, measured by the CMB, and the faster local rate, measured by supernovae. The weaker gravity inside the void allows space to expand faster, making nearby galaxies appear to recede quicker, thereby inflating our local Hubble constant. This explanation resolves the tension without needing to invent exotic, new particles or forces. However, this simple resolution comes at the high cost of undermining Einstein's core philosophical principle. If we accept that the universe is not uniform, it doesn't just necessitate a tweak to a parameter. It challenges the very geometry of space itself. This has led some physicists to suggest that the cosmological principle must be modified, that it is merely a good approximation that fundamentally breaks down under certain low-density conditions. If true, it would mean that cosmology cannot be perfectly described by a single global model. Instead, each vast region of space might follow slightly different expansion dynamics depending on its local density and curvature. The search for this breakdown is driving the next generation of missions. ESA's Euclid and the Dark Energy Spectroscopic Instrument, DESI, are meticulously mapping billions of galaxies to check whether the large-scale structure remains statistically uniform beyond the KBC region. If they find persistent large-scale variations, that would serve as the first irrefutable observational signal of the cosmological principle's failure. Furthermore, the James Webb Space Telescope, JWST, by peering deep into the earliest epochs of the universe, observes galaxies forming less than $300 million years after the Big Bang. If the distribution of those ancient galaxies appears clumpier or more uneven than models based on uniformity predict, it would mean the seeds of our modern colossal voids were planted from the very earliest moments of cosmic history. The unsettling realization that our cosmic address might not be typical leaves cosmologists deeply uneasy. The entire observational framework depends on the assumption that Earth's view is not special. The moment that assumption fails, every equation calibrated to it, distances, ages, expansion rates, may need fundamental recalibration. As one astrophysicist noted, if we are inside a giant void, then everything we infer about the universe, from its rate of expansion to its fate, could be an illusion of perspective. The universe is not playing a trick on us, but it is revealing that our measurements are inherently context-dependent. The cosmos is not a smooth, monolithic fabric. It may be an uneven mosaic expanding differentially, with vast empty patches like cosmic lungs breathing faster than the rest. And the KBC void might just be one of those lungs expanding quietly, distorting our measurements and challenging the long-held belief that we occupy no special, arbitrary place in the cosmos if we truly are breaking Einstein's rule. The consequences reach far beyond mathematics. It means the universe is not just uneven, it's asymmetric, with regions evolving under different gravitational and expansive pressures. This isn't just about finding a flaw in our models, it's about realizing that the ultimate structure of existence is more complex and less smooth than we dared to imagine. Whether the universe is governed purely by Einstein's equations, or if it is guided by deeper, unseen forces, the fact remains that the evidence of our local environment forces a profound reckoning with the most fundamental principle of cosmology. The final answer lies in the data, waiting to reveal whether uniformity reigns supreme or if our universe is a grand, beautiful exception to the rule. What if the universe is lying to us about its age? What if the numbers we've trusted for decades, the cosmic timeline that dictates the entire history of existence, are quietly betraying us? For nearly a century, cosmologists have believed the universe to be $13.8 billion years old. That foundational value comes from two sources: precise measurements of the cosmic microwave background, CMB, the leftover light from the Big Bang, and the Hubble constant, which defines exactly how fast space is expanding today. This established timeline gives us a coherent story of cosmic history, from the formation of the first hydrogen atoms to the eventual ignition of the first stars. But if our local expansion rate, the one measured around the Milky Way using nearby galaxies, is correct, ONSIM 73 I-text, kilometers per megaparsec, and the global rate measured from the CMB is TALOFASIM 67 log text, T kilometers per megaparsec, dollars. That profound 19% dollar mismatch between these two numbers throws the entire timeline into crisis. If we take the faster local rate as the true global average and run the equations of cosmic expansion backward, the calculated age of the universe becomes significantly younger, closer to 12.7 billion years. That $1.1 billion year gap might sound small, but it breaks everything we thought we knew about cosmic history. It creates a massive puzzle known as the cosmological age crisis. The problem is immediately visible when we look at the oldest inhabitants of the cosmos. Some of the oldest known star clusters, such as HD 150283, nicknamed the Methuselah star, are estimated to be nearly $13 billion years old. If the universe were only $12.7 billion years old, then these stars would appear to be older than the universe itself, an absolute logical contradiction. NASA's Hubble and ESA's Gaia missions have refined these stellar measurements over years of observation, confirming that many ancient globular clusters orbiting our galaxy date back to the first few 100 million years after the Big Bang. Yet, if the universe truly expands faster here, that cosmic clock no longer fits. So which measurement is fundamentally flawed? The stars or the universal scale of time itself? To resolve this, astronomers meticulously compare two cosmic yardsticks, the early universe, measured by the CMB, and the local universe, measured by nearby supernovae. The Planck satellite gave us one of the most detailed portraits of the early universe ever made, mapping the fluctuations in the CMB down to microkelvin precision. From that data, cosmologists derived the slower expansion rate of Sim 67 Tarrant text Tarrant countess per megaparsec, and the stable $13.8 billion year age we have relied upon for so long. But when NASA's Hubble Space Telescope and JWST measured more recent supernovae, they found space accelerating faster, inevitably forcing a younger calculated age of $12.7 billion years. Both methods are scientifically sound, relying on precise physics, but they cannot both be globally correct. This growing mismatch is the cosmological age crisis. As astronomer Wendy Friedman, a pioneer of cosmic distance measurement, put it, either we don't understand something about the physics of the early universe, or something is wrong with how we measure the local one. And indeed, the discovery that we reside inside the KBC void provides a plausible explanation for the latter possibility. If we live in this cosmic void, our corner of the universe may be expanding faster simply because it contains less matter, and thus has weaker gravity to resist dark energy. This weaker gravity would make galaxies appear to recede faster, artificially inflating our local Hubble constant to Sim 73 I-text equals per megaparsec. If that's the case, then the true global expansion rate and the true age of the universe might still be closer to the older value of $13.8 billion years, meaning the universe isn't lying. We are just misinterpreting the local context. However, the problem deepens when considering the stunning findings from the James Webb Space Telescope, JWST. JWST has begun to detect fully formed galaxies at record-breaking distances, some as far back as redshift Z-approx 13 meaning they existed when the universe was less than $350 million years old. These galaxies are too massive, too evolved, and too bright for a universe that young. If the universe were only $12.7 billion years old, there would have been even less time for those galaxies to form. Yet, JWST sees them in abundance. As one NASA astronomer noted, it's like finding fully grown adults in a nursery. The data is telling us that our understanding of how fast matter can organize itself into stars and galaxies is profoundly incomplete. The age crisis forces astronomers to explore hybrid models. Some involve a temporary burst of faster expansion in the earliest moments, an early dark energy phase that would allow galaxies to form sooner without drastically changing the overall age. Others explore modifications to gravity itself, where cosmic expansion evolves differently in low-density regions like ours. Both ideas are being tested by simulations running on supercomputers at NASA and ESA. Meanwhile, the possibility that dark energy isn't constant remains a powerful contender. Einstein described it as an unchanging cosmological constant. But if dark energy actually evolves over time, growing stronger as the universe expands, it could make the expansion appear faster now than in the past. ESA's Euclid mission, launched to investigate exactly this question, will map how galaxies cluster and voids expand over billions of years, attempting to see whether dark energy's strength varies, a discovery that would rewrite the laws of physics themselves. Yet even with these advances, the simplest explanation remains the most haunting. Perhaps the universe isn't deceiving us. Perhaps we are misunderstanding where we stand inside it. Living in an expanding void could naturally make our clocks run slightly differently, our distances appear stretched, and our cosmic age seem younger than it truly is. This wouldn't mean physics is broken, only that it is more local and context-dependent than we thought. Einstein's relativity already tells us that time and space change depending on gravity. Inside a low-density region, time runs a little faster, light travels a little farther, and distances expand a little quicker. In that case, the universe may simply be revealing that our measurements depend on context, but for now, the crisis remains unsolved. The most precise instruments ever built, from Hubble and Planck to JWST and Euclid, disagree by just enough to keep cosmologists awake at night. The universe still refuses to reveal its true age with absolute certainty. As astrophysicist Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to us." Perhaps this mystery, this sliver of uncertainty, is what keeps science alive. Every new discovery pushes the boundary of what we know, but also deepens the shadows beyond it, forcing us to question the very timeline of existence itself. The stubborn insistence of the cosmic voids, regions like the KBC void that are too large, too empty, and expanding too quickly to fit comfortably within the standard model of cosmology, has led physicists to ask one of the most dangerous and thrilling questions in modern science. What if Einstein's gravity, the very foundation of all modern physics, simply stops working at the edge of the universe? This is the core hypothesis of modified gravity, suggesting an alternative explanation for cosmic acceleration that doesn't rely entirely on the mysterious concept of dark energy. For more than a century, general relativity has passed every test with elegant precision. It accurately explains the orbits of planets, the bending of starlight near the Sun, and the ripples of space-time from colliding black holes. Yet, when we zoom out to the largest scales, billions of light-years across, the universe begins to behave as if gravity itself is subtly changing its mind. Inside vast, underdense regions like our KBC void, galaxies drift apart faster than Einstein's equations, coupled with the known amount of matter and dark energy, seem to predict. To account for these immense accelerating hollows, some physicists have begun to hypothesize that gravity doesn't follow the same rules everywhere. The law of attraction may be an approximation of a deeper, scale-dependent force. The idea behind modified gravity is that Newton's and Einstein's laws, while perfectly accurate on scales from a solar system to a galaxy cluster, might be incomplete when the gravitational pull becomes extremely weak, such as in the deep vacuum of a cosmic void. One of the best-known examples of this idea is MOND, or modified Newtonian dynamics, proposed by physicist Mordechai Milgram in the 1980s. Mond suggests that at extremely low accelerations, like those inside cosmic voids, gravity becomes stronger than expected, making structures hold together without needing the vast amounts of invisible dark matter that the standard model requires. In Milgram's own words, if you change the law of gravity at very small accelerations, you can explain how galaxies rotate without invoking invisible matter. While Mondi was primarily designed to solve the mystery of galaxy rotation curves, the observation that stars orbit faster than the visible mass can account for, its implications stretch far beyond individual galaxies. If gravity truly strengthens in low-density regions in a way Mond describes, the same initial fluctuations that seeded the cosmic web could grow into deeper and larger underdensities over billions of years, potentially allowing for the natural formation of supervoids like the KBC without violating the overall balance of the universe. The uniform matter distribution confirmed by Planck and WMAP in the early universe, which seemed too smooth to produce such enormous modern voids, might naturally lead to them under a Mond-like framework where gravity's strength changes with local density. However, applying Mond to the complex, expanding the cosmos is tricky because Einstein's equations are fully relativistic, and Mond in its original form was not. To bridge that gap, physicists developed TVES, tensor vector scalar gravity, a relativistic extension of Mond proposed by Jacob Bekenstein. In TVES, gravity arises from multiple interacting fields, not just the curvature of space-time, the tensor field, but also supplementary vector and scalar components that modify gravity's strength depending on the environment. In regions rich with matter, TVES behaves almost exactly like general relativity. But in cosmic voids where matter density is low and gravitational acceleration drops below a critical threshold, such as Sim 10 on text MS2, the scalar field amplifies the gravitational pull, creating conditions that could explain the immense structure and persistence of the KBC void. The upcoming Euclid mission is expected to provide one of the strongest tests yet for these models. By meticulously measuring how galaxies are distributed across cosmic voids and filaments, Euclid will check whether gravitational lensing, the bending of light, and galaxy flow patterns match the strict predictions of general relativity, or if they subtly diverge toward predictions made by modified gravity. If Euclid finds that voids expand faster or bend light differently than Einstein's theory predicts, it could mark the first observational evidence of new gravitational physics, a revolutionary discovery that would necessitate rewriting one of the most fundamental laws of nature. NASA's JWST is also contributing, albeit indirectly, by observing galaxies at high redshifts, Zeta $10. JWST reveals that massive structures formed earlier and faster than the Taust Lambda CDM model allows. If gravity was slightly stronger in low-density regions, as Mond suggests, those early galaxies would have assembled more efficiently, potentially matching JWST's surprising findings. Still, not all scientists are convinced. Mond and its relatives face their own persistent problems, such as struggling to explain the full dynamics of galaxy clusters or the precise pattern of fluctuations in the CMB. The Standard Model, despite the Hubble tension, remains far more successful overall. But the persistence of modified gravity models speaks to a deeper unease in cosmology. Our theories still cannot easily reconcile the behavior of gravity on small, precise scales with its behavior on large cosmic scales. Gravity works flawlessly near stars and black holes, yet it stumbles when describing the cosmic web and its gigantic voids. Modified gravity isn't limited to Mond. There are families of alternatives like AFR's gravity and other scalar tensor theories that propose the curvature of spacetime itself changes with local density, allowing voids to expand more freely. Detecting the effects of these hidden fields would mean uncovering the first real signs of quantum gravity acting on cosmological scales. So the verdict remains open. General relativity still stands unbroken, but its edges are beginning to blur, softened by the vast silent evidence of the cosmic voids. If these voids truly hint at new gravitational laws, it would mean that the curvature of spacetime isn't a fixed rule, but a flexible relationship that depends on environment, energy, and scale. Einstein's theory would remain correct locally, but incomplete at cosmic distances. The universe would no longer be governed by one simple equation, but by a layered set of gravitational behaviors. It is a thrilling and unsettling idea that the most universal force in existence might not be universal after all, revealing itself not in light and matter, but in the deepest, most impossible emptiness, the stubborn anomalies of the cosmic web. The existence of supervoids like the KBC and the persistent mismatch in the universe's expansion rate have forced cosmologists into a global, high-stakes campaign to test the very limits of the gravitational law. This campaign centers on the new generation of space and ground-based instruments, primarily the European Space Agency's Euclid mission and NASA's James Webb Space Telescope, JWST, which are actively engaged in testing gravity's law to determine if these voids are mere statistical oddities or the first direct signs of new physics operating across cosmic scales. The crisis stems from the realization that if gravity, as described by Einstein's general relativity, is the whole story, structures like the KBC void should be astronomically rare. They are too large, too empty, and expanding too quickly to have formed easily from the tiny quantum fluctuations left by the Big Bang. The hypothesis of modified gravity, which suggests that gravity changes its behavior in the low-density environment of a void, offers a theoretical solution. But to validate this, scientists need data of unprecedented precision across vast cosmic volumes. The Euclid mission, launched in 2023, is explicitly designed to meet this challenge. Its primary goal is to investigate the balance between gravity and dark energy by mapping the three-dimensional positions and subtle shapes of over 2 billion galaxies across more than a third of the sky and over 10 billion years of cosmic history. Euclid's instruments, the Visible Imager, VIS, and the Near-Infrared Spectrometer and Photometer, NISP, are engineered to detect minute distortions caused by weak gravitational lensing. This effect, the slight bending of light as it passes through the mass of large-scale structures, reveals where matter, both visible and invisible dark matter, is distributed. If gravity behaves differently in the deep voids than Einstein's theory predicts, Euclid will see it. The amount of light distortion around voids and filaments will either perfectly match general relativity's predictions or subtly diverge toward the predictions of modified gravity models. For instance, models of modified gravity, such as extensions of MOND, modified Newtonian dynamics, predict that the gravitational potential inside voids should behave differently, allowing them to expand faster and grow larger. If Euclid finds that the rate at which voids grow over time is accelerated compared to the predictions of the standard lambda CDM model, that will serve as powerful, direct evidence that a modification to gravity is necessary at these large, low-density scales. Euclid's massive census of galaxies will also allow cosmologists to chart the evolution of baryon acoustic oscillations, BAO, patterns across various environments, testing whether the cosmic ruler is stretched unevenly inside voids, a key signature of the local expansion bias. Meanwhile, the James Webb Space Telescope, JWST, contributes to this investigation from a different, equally vital angle, the early universe. JWST is capable of peering back to the first few 100 million years after the Big Bang, observing galaxies at record-high redshifts, e.g. Z 10 $. These observations provide a crucial baseline, revealing how quickly structure, the first galaxies and their surrounding matter, formed when the universe was in its infancy. JWST has already revealed massive, fully formed galaxies that appeared faster than many ton lambda CDM simulations predicted, this unexpected accelerated organization of matter in the early cosmos could hint at stronger or modified gravitational physics operating during the universe's infancy. If gravity was slightly stronger in low-density regions, as some Mond variants suggest, or evolved faster in general, it would explain why these early galaxies assembled more efficiently, potentially bridging the gap between JWST's surprising findings and the current theoretical models. Furthermore, these powerful instruments work in concert to challenge the notion of a uniform universe. The data from JWST's deep fields combined with Euclid's wide-field mapping will allow scientists to see if the large-scale structure remains statistically uniform beyond the KBC region. If they find persistent variations, it would confirm the breakdown of the cosmological principle. The ultimate goal of this testing campaign is to determine whether dark energy is truly a uniform constant, as represented by T lambda dollars in Einstein's equations, or if it is a dynamic field, quintessence, or a manifestation of modified gravity. If voids are found to amplify the expansion rate significantly, it could be interpreted either as dark energy being stronger in low-density regions, or as gravity being weaker in those regions, or perhaps a combination of both. The current evidence, though strong, remains a stress test, not a definitive refutation. As NASA cosmologist Adam Rees reminds us, gravity has never failed us yet. But the data persists. The largest voids remain anomalies. The possibility remains that gravity is influenced by hidden fields, scalar or tensor fields, that subtly alter the curvature of spacetime in regions of low density. Detecting the effects of these hidden fields would be the first real sign of quantum gravity acting on cosmological scales. So, for now, the verdict remains open. General relativity still stands unbroken, but its edges are beginning to blur, softened by the vast, silent evidence of the cosmic voids. If future observations from Euclid, JWST, and the Vera C. Rubin Observatory confirm modified gravity, the implications would be revolutionary. It would mean that the most universal force in existence might not be universal after all, and the next great revolution in physics won't come from colliders or black holes, but from the most unexpected place of all, the emptiness between galaxies. The quiet revelation that we inhabit a cosmic desert, a vast cavity like the KBC void, leads us to the question of origins. What if the largest structures in the universe, those billions of light-years across, were born from ripples smaller than an atom? This profound connection between the subatomic realm and the cosmic scale is the story of the quantum blueprint, revealing how the deepest structures, including the seeds of nothing themselves, were scripted at the moment of creation. The entire observable universe, in its first tiny fraction of a second after the Big Bang, specifically, within 10 to 35 seconds, underwent a period of dramatic, exponential growth known as cosmic inflation. During that instantaneous growth spurt, the universe expanded by a factor of at least 10 to 26 dollars, meaning space itself ballooned faster than light could traverse a single atom. In that violent yet essential instant, something truly remarkable happened. Quantum fluctuations, the random, microscopic variations in energy that are inherent to space-time itself, were stretched across space to monumental cosmic scales. Those tiny irregularities became the indelible seeds from which every galaxy, cluster, and, crucially, every void we see today eventually formed. It's almost impossible to grasp the scale of this transformation. A fluctuation that began as a mere whisper of quantum uncertainty, magnified by inflation, could grow over $13.8 billion years into a vast cavity spanning 2 billion light-years, like the KBC void that surrounds us today. As the father of inflation theory, cosmologist Alan Guth once famously said, "Quantum fluctuations are the seeds of all structure in the universe." NASA's WMAP and ESA's Planck missions both captured this primordial fingerprint in the cosmic microwave background, CMB. The Planck satellite mapped faint patterns of temperature variations, only one part in $100,000, that reveal the very first blueprint of structure, frozen when the universe was just 380,000 years old. The bright and dark patches on those maps mark where matter was just slightly denser or thinner than the cosmic average. Those faint blue regions on the map were ever so slightly less dense, and they are the direct ancestors of today's enormous supervoids. That means the vast emptiness around us isn't random. It's a frozen memory of the universe's initial quantum birth. The underlying physics for this lies in quantum field theory. Even in a vacuum, fields like the inflaton, the hypothetical field that drove inflation, experience spontaneous fluctuations in energy. Normally, these fluctuations are fleeting and cancel out quickly. But the rapid, exponential expansion of inflation stretched them so quickly that they became macroscopic, freezing them permanently into the very fabric of space-time. When inflation ended, these energy variations translated directly into subtle differences in matter density, which then began to shape the entire cosmic web. Over billions of years, gravity took over, performing its long, patient work. Matter in the slightly denser zones slowed local expansion and condensed, pulling in surrounding material to form the filaments, clusters, and stars. In contrast, the underdense regions, the future voids, expanded faster, pulling galaxies outward and thinning even further over time. The structure of today's universe is truly written in the quantum noise of its beginning. When cosmologists simulate structure formation under the standard lambda CDM model, they start by inputting those same measured CMB fluctuations. Over cosmic time, dark matter clumps in the denser zones, pulling normal matter along with it, while the underdense regions naturally expand faster, becoming the voids we observe. The scale of these voids depends directly on the amplitude of those initial quantum fluctuations. Our own KBC void, with its 20% lower than average matter density, may trace back to a patch of space that was just 0.0% less dense than its surroundings during inflation. Such an infinitesimal difference, magnified over $13.8 billion years, became the vast cosmic desert we now inhabit. The simulations run by projects like the illustrious TNG project reproduce this process perfectly. The resulting images match observations from surveys like SDSS and DESI almost perfectly. Vast, empty voids surrounded by intricate, interconnected filaments of glowing matter. That high level of agreement confirms that quantum fluctuations alone can explain the origin of both the largest and emptiest structures we observe. It also reinforces the idea that the universe, while seemingly chaotic on a regional basis, follows the simplest possible rules, tiny random variations magnified across unimaginable scales. However, there is a deeper puzzle that keeps the possibility of new physics alive. The Planck satellite found the CMB to be slightly asymmetric. One side of the sky appears just a bit cooler and smoother than the other. This hemispherical anomaly might suggest the quantum seeds themselves weren't perfectly random, or that inflation had a specific directionality. If true, that would hint that the universe's earliest fluctuations carry traces of physics beyond the standard model, perhaps even signatures of multiverse dynamics or primordial gravitational waves. NASA's BICEP and SPT experiments at the South Pole are actively hunting for faint, curling patterns in the CMB's polarization, the definitive proof of gravitational waves from inflation. If detected, they would confirm that quantum fluctuations did not just create structure, they also imprinted gravity's first heartbeat onto space itself. ESA's Euclid and NASA's JWST will continue this search by observing how voids evolve today. If their rate of expansion and shape distribution match the predictions of inflation, we'll know that even the emptiness we see now was scripted by quantum mechanics in the universe's first instant. It's astonishing to think that the cold, silent expanse of the KBC void, 2 billion light-years of near nothing, began as a fluctuation smaller than a proton. Every galaxy, every star, every pocket of emptiness is the magnified echo of those ancient quantum ripples. That whisper, stretched by inflation, became the cosmic desert we now float within. The fact that randomness at the smallest scales can sculpt order across the largest is the core legacy of the quantum blueprint. What if the echoes of the Big Bang are still rippling through space, and those ancient sound waves are quietly telling us that the region we live in is emptier than it should be? This profound connection between the universe's earliest acoustic vibrations and our current cosmic address is the story of the silent echo, revealing how a phenomenon called baryon acoustic oscillations, BAO, provides an immovable, stretched cosmic ruler that traces the shape of our local void. Roughly 400,000 years after the Big Bang, the early universe was filled not with stars or galaxies, but with an incredibly dense, hot plasma, a sea of protons, electrons, and photons all tightly coupled together. In that chaotic, pressurized soup, pressure and gravity were locked in a constant, dramatic battle. When gravity pulled matter inward toward tiny, dense quantum fluctuations, the seeds of future galaxies, the intense radiation pressure pushed it violently back out. The result was a series of expanding and contracting pressure waves, the first true sound waves in cosmic history. Today, we call the fossilized imprint of these waves baryon acoustic oscillations, or BAO, and though the actual sound has long faded, its rhythmic pattern remains frozen in the way matter, specifically galaxies, is distributed across the cosmos. Every wave that once echoed through that early plasma left behind a preferred distance between galaxies, a fixed length that cosmologists can still measure today, which is approximately 490 million light-years. This faint, regular spacing acts like an unchanging cosmic ruler, a standard yardstick for mapping how space itself has stretched and expanded over the billions of years since. When researchers applied this cosmic ruler to the region immediately around our galaxy, they noticed something subtly strange yet fundamentally important. The distances between galaxies here are slightly larger than expected. The imprint of those ancient sound waves seems stretched, as if space in our local neighborhood has expanded a little faster than the global average. This subtle distortion is one of the strongest pieces of evidence confirming the reality of the KBC void, the immense underdense region about 2 billion light-years across that includes the Milky Way and much of our local universe. In simple terms, BAO measurements are telling us that we live inside a bubble where the density of matter is roughly 20% lower than the cosmic average. This underdensity means weaker gravity, which allows the void to expand faster, thereby stretching the BAO signal. NASA describes this phenomenon as a fingerprint of sound from the infant universe, preserved like frozen ripples on the surface of time. Each stretched wave shows how matter moved before the first stars even formed. To detect these incredibly subtle patterns, astronomers rely on massive, painstaking galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, the Dark Energy Spectroscopic Instrument, DESI, and the Euclid mission. These projects measure the positions and redshifts of millions of galaxies to chart their distribution in 3 dimensions. When scientists compare those maps to theoretical models of an even homogeneous universe, they find that our local region doesn't quite fit. Galaxies in our area are on average farther apart, not because of observational error, but because the space between them has expanded more rapidly. That is the BAO signal stretched by the void. As Amy Barger, one of the original discoverers of the KBC void, explained, if we're inside a large, underdense region, light from distant galaxies has to climb out of it, which alters how we perceive cosmic expansion. This means the Hubble constant, the number describing how fast the universe expands, appears different depending on where you measure it. In denser regions, the expansion looks slower. In emptier regions like ours, galaxies appear to recede faster. And the stretched BAO patterns confirm this crucial point. the universe's expansion isn't completely uniform. To picture what these acoustic oscillations once were, imagine the early universe as a glowing fluid sphere. Tiny overdensities, the miniature seeds of future galaxies, were the source of these waves. As intense radiation pressure pushed outward, spherical sound waves rippled from each seed at about half the speed of light. When the universe cooled enough for neutral atoms to form, the point of last scattering, these ripples instantly froze into the cosmic structure we see today. Every galaxy cluster and void we observe is the fossilized remnant of those pressure waves. And inside our own cosmic void, those fossilized distances are slightly larger, a silent, measurable record of faster local expansion. In 2021, the Dark Energy Survey mapped over 226 million galaxies and confirmed that BAO patterns align perfectly with regions of varying density, just as theory predicts. When the BAO data was applied specifically to the KBC void, the results strongly supported a local underdensity large enough to explain at least part of the persistent Hubble tension. It is truly remarkable that sound, a phenomenon that can no longer travel through space today due to its low density, once literally shaped the entire universe. Astronomers often describe BIO as the heartbeat of the cosmos, a rhythm frozen into the geometry of the universe itself. When we measure that rhythm and find it offbeat in our neighborhood, it is like discovering that our part of the cosmic symphony is playing at a different, accelerated tempo. Yet that offbeat tempo tells a consistent story, that we live in a quieter corner of space where the great wave of creation stretched a bit further than elsewhere. The more precisely we measure these acoustic waves, the clearer the shape of our cosmic home becomes. This isn't just an academic pursuit. It's how we accurately locate ourselves in the vast three-dimensional map of space and time. If future data from JWST, DESI, and Euclid confirm that our BAO patterns are definitively stretched, then the KBC void isn't just a curiosity. It's a fundamental piece of cosmic architecture. It means our place in the universe is rarer than once believed, not central, but uniquely distorted by the geometry of emptiness. And that understanding may rewrite how we interpret every redshift, every galaxy count, and every estimate of cosmic age. Even the $13.8 billion-year timeline could shift slightly, depending on how deeply this void affects local expansion. It is a quiet realization that the universe's first sound waves are still speaking to us across the dark. We just had to learn how to listen to their silent echo. What if everything we've ever known, the Milky Way, the Andromeda Galaxy, the Virgo cluster, and 100,000 others, is not part of a grand cosmic structure anchored immovably in dense matter, but is instead drifting freely inside a vast hollow of space? The largest gravitational structure that encompasses our galactic home is the Laniakea supercluster, a breathtaking formation that spans over 500 million light-years and contains roughly 100,000 galaxies, possessing a total mass equivalent to 1017 suns. Yet despite its colossal enormity, recent measurements show that this entire, immense structure resides completely within the boundaries of the KBC void, a region of the cosmos almost 4 times larger than Laniakea itself. This presents a striking paradox that challenges our intuition. The floating continent, a massive gravitational entity existing inside a region that is by definition profoundly underdense. To understand how something as massive as Laniakea can exist and maintain coherence in such a place, we must revisit the groundbreaking work of astronomers R. Brent Tully and Hélène Courtois. In 2014, they published a landmark study mapping the local motions of over 8,000 galaxies, revealing that all nearby galaxies, including our Milky Way, belong to one immense basin of attraction, a gravitational continent they named Laniakea, meaning immeasurable heaven in Hawaiian. The galaxies in this region don't orbit a single fixed center. Instead, they flow along curved paths, shaped by both attraction and repulsion, drawn inward toward the great attractor and, crucially, pushed outward from the underdense region now identified as the local void. Tully summarized it beautifully. Our home's supercluster is defined not merely by the galaxies themselves, but by the patterns of their motion through space. But when cosmologists combined this velocity map with large-scale density data, they realized the startling truth. The Laniakea supercluster, along with its neighboring structures, is embedded within a gigantic underdensity extending roughly 2 billion light-years, the KBC void. In other words, we are living not in the cosmic average, but in a bubble, a gravitational valley in the fabric of the universe, where gravity is weaker and expansion is faster. Inside this valley, Laniakea functions as a ridge of matter floating within the void, like a coral reef rising inside a deep oceanic trench. Simulations, such as those from the illustrious TNG project, confirm that voids are not perfectly empty. They contain faint filaments of dark matter and thin streams of galaxies, relics of the early universe that survived the rapid expansion of the underdense regions. These faint filaments can host entire superclusters, which are gravitationally bound yet surrounded by accelerating nothingness. The coexistence is a matter of local coherence. Gravity still holds Laniakea's galaxies together locally, preventing them from drifting apart, but the overall space around them is stretching faster than it does elsewhere. According to ESA's Planck mission, the universe's average density is only about 6 protons per cubic meter. Inside the KBC void, that value drops by nearly 20%. That difference is enough to alter how gravity and expansion interact within Laniakea. As NASA's cosmologist Michelle Thaler once said, "Galaxies are like islands. In a rising tide they stay together, but the ocean of space between them grows. The dark matter halos act like the vital glue, preventing galaxies from drifting apart, even as dark energy stretches the fabric around them. The motion itself paints a vivid picture of this imbalance. Galaxies inside Laniakea move coherently, following the precise contours of the gravitational potential. On one side, they fall toward denser regions like the Shapley supercluster. On the other hand, they are actively pushed outward by the local void's lower density. This push and pull defines our cosmic motion, a delicate balance between attraction and expansion. The local group, which contains the Milky Way, drifts at an astonishing speed of about 630 our text, km solons relative to the cosmic microwave background. ESA's Gaia mission has refined this measurement, confirming the direction of flow identified by Tully and Courtois, movement away from the local void and toward the greater attractor regions. This continuous shared motion reveals that Laniakea is not a static structure anchored in space, but a dynamic current of galaxies drifting along the gradient of cosmic density, a gentle fall through an uneven ocean of space-time. And this localized motion may be the very reason we see the Hubble tension. If our supercluster is floating inside a void, the expansion we measure will naturally appear faster than the global average. We are measuring the universe from inside a rising tide. Simulations based on the KBC model predict that living inside such a void can inflate the local expansion rate by 5 to 7%, enough to explain a significant part of the observed difference. It's not an error. It's perspective dictated by position. The stability of Laniakea, despite being immersed in a region of accelerated expansion, is a testament to the power of dark matter. The structure remains gravitationally coherent. Its galaxies, though separated by millions of light-years, share a collective motion as though bound together by invisible, resilient filaments of dark matter. As cosmologist Daniel Pomerade explains, the voids are not empty. They are where the universe reveals its shape most clearly. When viewed in 3D, the Laniakea supercluster resembles a luminous ridge drifting at the edge of a deep depression. the KBC void itself. Like a raft on a cosmic current, it floats between gravitational basins, pulled by one side and released by the other. The more we map, the clearer it becomes. The universe's architecture is not static. Superclusters, filaments, and voids form a living flow, an interconnected circulation of matter shaped by dark energy's invisible hand. Even our home, the Milky Way, is not fixed. It's gliding along this flow, drawn toward Shapley, escaping the local void and ultimately drifting through an expanding cosmic desert. As Carl Sagan once said, "We are adrift in a great cosmic ocean." And for the first time, we are beginning to see the ocean's currents, confirming that our supercluster is indeed a floating continent in the midst of a great, accelerating cosmic hollow. The persistent puzzles posed by the cosmic voids, regions of profound emptiness that are larger and expanding faster than the standard cosmological model predicts, force us to confront the biggest mystery of all: dark energy. What if the emptiest regions of the universe are not just quiet spaces, but active laboratories where the laws of physics themselves begin to subtly shift? This quiet speculation suggests that dark energy, the mysterious force driving the universe's accelerated expansion, might not behave the same everywhere. This is the hypothesis of dark energy dynamics, suggesting the universe is governed by inhomogeneous expansion. Dark energy makes up nearly 70% of all cosmic energy. We know it dominates the dynamics of the cosmos, yet we've never observed it directly. We only see its relentless fingerprints, galaxies drifting apart, clusters receding faster than gravity alone could allow, and light stretching as space itself grows. In the standard top-lambda CDM model, dark energy is treated as the cosmological constant, lambda dulles, a steady, unchanging pressure that fills all of space equally. But as astronomers peer deeper into the universe with powerful new telescopes like the JWST and Euclid, a profound question is rising. What if that constant isn't constant at all? The idea of dynamic dark energy, sometimes called quintessence, suggests that this mysterious energy may evolve over time, or, crucially, vary with environment. If that is true, then the vast cosmic voids, places where gravity weakens and matter nearly vanishes, are the perfect places to test it. Inside a void, matter density is up to 20% lower than average, meaning there's far less gravity to counteract expansion. In such places, dark energy's effect becomes dominant, stretching space more efficiently, as though freed from gravity's heavy resistance. This makes voids natural accelerators of expansion, cosmic test chambers where dark energy reveals its true, unfiltered power. In 2015, ESA's Planck satellite mapped the cosmic microwave background, CMB, and confirmed the universe's accelerated expansion, but its measurement of the Hubble constant, SUTSIM 67.44 E-text, kilometers per megaparsec, conflicted sharply with local measurements. Near Earth, SIM 73 high-text, kilometers per megaparsec, while as one possible explanation is precisely that dark energy might behave differently in low-density regions like our own. Inside the KBC void, dark energy's influence could be amplified, creating the illusion of a faster local expansion rate, thereby explaining the persistent Hubble tension. ESA's Euclid mission, launched in 2023, was designed specifically to investigate this. How do dark energy and gravity interact across cosmic structure? By mapping over 2 billion galaxies across 10 billion years of history, Euclid measures subtle distortions caused by weak gravitational lensing. If dark energy varies across space, Euclid should detect it. Voids, in particular, are expected to show an enhanced local expansion rate compared to denser regions. By comparing the shapes of voids at different distances, effectively different epochs of time, scientists can test whether the influence of dark energy grows or fades depending on the local environment. NASA's Dark Energy Survey, DES, has already provided tantalizing hints. By analyzing thousands of cosmic voids, researchers found that the rate of galaxy recession inside them slightly exceeds the predictions of the standard Dowd-Lambda CDM model. These supervoids appear to expand faster than average, a critical clue that dark energy might be stronger in emptier regions. As astrophysicist David Hogg of NYU commented, "If dark energy isn't constant, the voids will be the first to show us." Why? Because in these regions there's almost nothing left to resist expansion. Gravity weakens as matter thins out, so dark energy takes over, not gradually, but absolutely. The difference might be subtle, a few percent variation in expansion rate, but over billions of light years and billions of years, that small change profoundly reshapes the geometry of the universe itself. A model that describes this phenomenon is the inhomogeneous dark energy model, where the energy density of dark energy depends on the local curvature of spacetime. In regions of strong curvature, dense clusters, dark energy's influence is suppressed. In flatter regions, voids, it grows stronger. If this model is correct, it would elegantly explain the Hubble tension. Our galaxy, residing in a massive void, experiences an amplified effect of dark energy. It would mean that cosmic acceleration is not a uniform process. It varies with environment. The universe doesn't expand evenly. It breathes differently from one region to another. But how could dark energy change from one region to another? One possibility lies in scalar field theories, where dark energy arises from a fundamental field permeating space similar to the Higgs field. Its value, and therefore its pressure, can vary slightly depending on local density. Inside voids, the field might relax toward higher energy states, increasing the local rate of expansion. Simulations based on these quintessence models show that even tiny fluctuations in the field's potential could produce the noticeable effects we see on void evolution, leading to the very pattern of accelerating pockets of emptiness that dominates our universe. This perspective transforms our view of cosmic emptiness. Voids are not dead zones. They are active stages where the expansion of the universe reveals its hidden tempo. And as Euclid, JWST, and the Nancy Grace Roman Space Telescope continue to probe deeper into these silent expanses, we may soon discover that dark energy is not uniform at all, that the force shaping the fate of the cosmos behaves differently depending on where you stand. If the voids truly amplify dark energy, then we are not just living in an expanding universe. We are living in one that learns how to expand differently. And that possibility leads to the next great mystery. If the largest structure that contains us is floating inside this accelerating void, what does that mean for the longevity and stability of the entire supercluster? What if the space between galaxies, the emptiness we once ignored, is far stranger and larger than we ever imagined? Astronomers used to believe the cosmos was evenly filled with matter on the largest scales, a smooth, uniform blend stretching endlessly in all directions. But as our telescopes grew sharper and our maps reached deeper, we found something deeply unsettling. Most of the universe is missing, replaced by a network of supervoids, enormous regions where matter density drops far below average, spanning hundreds of millions or even billions of light years. We live inside one of them, the KBC void, discovered in 2013, but it turns out we might not be alone. The cosmos may be peppered with an architecture of hidden hollows. This leads us to the mystery of hidden supervoids, exemplified by the Eridanus supervoid and its quiet thermal signature, the cold spot anomaly. Roughly 3 billion light-years away, in the direction of the constellation Eridanus, lies another colossal emptiness, the Eridanus supervoid. Its existence is linked directly to one of the strangest anomalies in modern cosmology, the CMB cold spot, a patch of sky that appears mysteriously colder than the expected uniform glow of the ancient cosmic microwave background, CMB. When NASA's WMAP satellite and later ESA's Planck satellite mapped the microwave afterglow of the Big Bang, they found that one region near the Eridanus constellation was about 70 microkelvin colder than the surrounding CMB. That difference might sound tiny, but on cosmological scales, it's enormous, spanning about 5 degrees across the sky, the equivalent of 10 full moons lined up side by side. The sheer size and depth of this cold spot were statistically almost impossible to explain based on the early universe's uniformity. The discovery immediately led researchers to wonder, could this profound coldness be caused by light traveling through a massive underdense region of space? If so, the void would have to be absolutely colossal. In 2015, a team led by Istvan Sapudi used galaxy and dark matter survey data to confirm it. They found a region roughly $1.8 billion light-years in diameter, where galaxy density drops by about 20–38%, matching perfectly with the cold spot's position. This supervoid, they realized, was the largest single structure identified in the visible universe at the time. This finding was a major milestone. It was the first real evidence that cosmic voids can leave a measurable thermal imprint on the oldest light in the universe. The explanation for this thermal shadow lies in the integrated Sachs-Wolf (ISW) effect. When a photon from the CMB passes through a dense region, it gains energy falling into the gravitational well and loses the same energy climbing out. But when it passes through a vast, accelerating void, the space itself expands while the photon is inside it. This rapid expansion causes the gravitational well to effectively decay or flatten slightly, so the photon doesn't regain all of its lost energy on the way out. The result, it exits slightly cooler than it entered. This phenomenon means that light traveling through a growing void gets stretched and chilled by the universe's acceleration. The cold spots are thus the physical signature of accelerated expansion operating unchecked in the deep voids. The realization that supervoids like Eridanus and the KBC exist in abundance sparked a revolution in large-scale structure studies. Astronomers began systematically hunting for them using data from surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, DES, and the new Euclid mission. The results were stunning. Voids are everywhere. Today, researchers estimate that voids occupy more than 80–90% of the total cosmic volume, leaving only the thin filaments of galaxies to form the vast cosmic web. The universe, in its truest form, is more like foam than fog, mostly empty with galaxies forming only along its fragile, interconnected edges. The very existence of multiple supervoids, especially those as large as Eridanus or KBC, poses a deep challenge to the standard lambda CDM model. The model predicts that voids of this size should be incredibly rare, occurring with a probability of less than 0.14% to occur by chance. The fact that we seem to have found at least 2 of these cosmic behemoths suggests that something fundamental about the distribution of matter in the early universe or the nature of dark energy might be different from what we thought. This has profound implications for the Hubble tension. If voids are more common or more massive than expected, they could be the key to understanding why local expansion appears faster. The Eridanus supervoid, while massive, is still only estimated to account for about 10–20% of the total observed temperature drop in the cold spot, suggesting that either the void is even larger or deeper than we can currently measure, or that the ISW effect is stronger inside supervoids than general relativity under standard tau lambda CDM parameters predicts. This latter possibility hints that the influence of dark energy might be stronger in emptier regions, leading to the hypothesis of dynamic dark energy quintessence. Every new telescope, from Euclid and JWST to the Vera C. Rubin Observatory, is turning its gaze not toward where galaxies are, but where they aren't. because in the absence of light, the universe might be telling its most important story. The cold spots on the ancient CMB are not random noise. They are the thermal echo of the KBC void itself and the Eridanus supervoid, the quiet fingerprints of where we are and how the universe is unevenly expanding around us. The greatest mystery of all is not what fills the universe, but what leaves it empty, revealing that the universe's architecture is a careful, active balance between matter and the expanding silence. What if every measurement we've ever made of the universe's expansion, every distance, every redshift, every fundamental constant is subtly wrong, not because of errors in our instruments, which are now astonishingly precise, but simply because of where we are? Astronomers call this possibility the Hubble bubble, a large region of space roughly 2 billion light-years across, where the Hubble constant, the measure of cosmic expansion, appears significantly higher than it does in the rest of the universe. In this zone, our local galaxies seem to drift away faster than expected, as if the cosmic fabric around us is stretching a little more eagerly. But beyond its edges, the expansion rate slows down, returning to the global average measured by the Planck satellite. If this effect is real, it could mean that our entire view of cosmic history, the very age of the universe, the rate of expansion, and even the effective strength of gravity have all been distorted by the bubble we live inside. We are, quite literally, immersed in a local distortion of cosmic time. To understand the tension, we have to start with the number that has relentlessly divided cosmology for years. The Hubble constant, a measure of how fast galaxies recede per unit distance, expressed in kilometers per second per megaparsec, kms per MPC. Local measurements, such as those made using the Hubble Space Telescope and JWST on nearby galaxies and supernovae, suggest a value around 73 km per MPC. But data from the ESA Planck mission, which studies the cosmic microwave background, CMB, the oldest light in the universe, yields a slower global rate around 67, 4 km per MPC. This significant disagreement, known as the Hubble tension, has become one of the biggest mysteries in modern cosmology. Why would the nearby universe appear to expand faster than the distant early universe? One possible answer lies not in mysterious new physics, but simply in our cosmic address. In 2013, astronomers Ryan Keenan, Amy Barger, and Len Cowie proposed that the Milky Way and its neighboring galaxies reside inside a massive underdense region, the KBC void, where matter density is about 20% lower than the cosmic average. Within such a region, gravity's pull is weaker, allowing the local space to expand more quickly than regions filled with more matter. It's like living in a slightly inflated pocket of the universe, a cosmic bubble expanding faster than the rest. Keenan and his team found that this bubble's scale, roughly 2 billion light-years in radius, matches the range where local Hubble measurements differ most sharply from the global ones. In other words, the so-called Hubble bubble might not be an illusion. It could be a real, physical feature of our environment, the visible boundary of our local void. Mathematics supports it. A void of the KBC's size and depth could boost the local expansion rate by 5 to 7%, exactly the amount needed to explain much of the observed discrepancy. This isn't coincidence, it's geometry. General relativity predicts that regions with lower density experience weaker gravitational deceleration and therefore faster expansion. Inside our bubble, space flows outward more freely. Outside, the denser cosmic walls pull it back. This dynamic picture is supported by data from the Sloan Digital Sky Survey, SDSS, which mapped millions of galaxies and revealed a vast underdensity stretching across hundreds of millions of light-years around our location, consistent with a local void. Even more compelling are the implications for gravitational lensing. Using weak lensing, the slight bending of light as it passes through matter, astronomers have reconstructed a mass map of our region, revealing a smoother, lighter web than average, with fewer massive galaxy clusters and more empty filaments, the precise hallmarks of an underdensity. In a sense, our cosmic neighborhood is unusually quiet. The same emptiness that gives us a clearer view of the universe may also be subtly skewing the very numbers we use to describe it. But the question remains: if we live inside a faster expanding bubble, what lies beyond its edge? Some cosmologists think there's a sharp boundary, a transition region where local expansion slows and the global average takes over. Others believe the change is gradual. ESA's Euclid telescope, launched in 2023, aims to find out by mapping galaxies up to 10 billion light-years away. It will measure how expansion varies with scale, testing whether the Hubble bubble is truly local or part of a deeper cosmic pattern. The more precise the data becomes, the sharper the disagreement remains. Could it be that both sides are right, that Planck measures the universe as a whole, while the local teams measure it from inside a unique, accelerating pocket? If that's true, it would mean the universe isn't uniform at the largest scales, a direct challenge to the cosmological principle, which assumes no location is special. Yet, all evidence points in that direction. We live in a slightly special place, not because of who we are, but because of where we are. Our instruments measure the light that passes through the void surrounding us, and that light carries the story of our bubble's faster expansion. Our perspective subtly tilts the universe we observe. If the KBC void is real and its expansion rate higher, then every constant, every distance, and every age we've measured could carry a hidden bias written into the fabric of our local sky. The possibility that the cosmos could be filled with pockets of space, each expanding at slightly different rates, suggests that the universal symphony is played with localized rhythms. This means our local bubble is inflating our perception of time and distance itself. The Nancy Grace Roman Space Telescope and future CMB experiments will help test this directly by measuring how expansion changes with direction, creating a new kind of cosmic weather map for the universe's growth. If anisotropies, directional dependencies, are confirmed, the standard cosmological model will require a fundamental rewrite. But for now, we can say this much with certainty. The region we inhabit, the space we use to measure the universe itself, is not average. It's an inflated bubble, a calm, expanding oasis, adrift in a vast cosmic sea. And beyond its edges, space slows and the universe breathes differently. It's humbling to realize that even our finest instruments cannot escape their cosmic neighborhood, and that every number we record carries the subtle fingerprint of our local void. Because sometimes the hardest thing to see clearly is the space we're standing in. The universe is not deceiving us. It's simply revealing that its measurements depend on context. The Hubble bubble, this local distortion, is a quiet reminder that the cosmos is a dynamic, uneven place, and we are precisely located within one of its most remarkable features. What if the calmest places in the universe, the vast cosmic voids, are also its most quietly creative? In the crowded regions of the cosmic web, galaxies collide, merge, and violently tear each other apart. Giant clusters like Coma or Virgo are places of constant high-energy violence where gravity crushes gas clouds, supermassive black holes ignite, and supernovae bloom like chaotic storms. But far away from those dense, messy crossroads in the quiet, immense hollows of the universe, the void, something profoundly different happens. There, gravity is weak, matter is sparse, and time itself seems to stretch a little longer between major cosmic events. Astronomers have found that these regions act as a void filter, creating an environment conducive to the slow evolution of void galaxies. Astronomers now know that voids make up about 90% of the volume of the observable universe. Even though they contain less than 10% of its galaxies, these regions are not completely empty. Faint galaxies drift through them, sometimes alone, sometimes in small, isolated groups. These are known as void galaxies, and they live under the gentlest gravitational conditions ever found. Observations from the Sloan Digital Sky Survey, SDSS, and NASA's GALEX mission show that these galaxies tend to be smaller, bluer, and richer in gas than their cluster counterparts. Many are still forming stars even now, $13 billion years after the Big Bang. In the silence of the void, star formation continues unhurried, undisturbed. It is as if the absence of pressure gives them the freedom to grow in peace, sheltered from the violent, disruptive forces elsewhere. The Euclid mission, designed to map dark matter and large-scale structure, has begun to refine our picture of these galactic oases. By tracing the positions and redshifts of millions of faint galaxies, Euclid's early results confirm what simulations had hinted at for years. Galaxies in voids evolve differently because their gravitational environment is fundamentally weaker. When matter is scarce, tidal forces, the gravitational stretches and pulls that distort galaxies in dense regions, are minimal. This means fewer galaxy mergers, fewer disruptions of orbiting gas, and far fewer starburst events violently triggered by collisions. Instead, star formation in void galaxies happens slowly and steadily, regulated primarily by the gentle cooling of interstellar gas. NASA's Spitzer Space Telescope and the JWST have both contributed key insights here. Spitzer's infrared imaging revealed that void galaxies often contain large reservoirs of cold hydrogen, the pristine raw material for stars that has never been stripped away by neighboring, larger systems. JWST's near-infrared spectra now show the detailed composition of these galaxies, detecting emission lines from young, metal-poor stars similar to those seen in the earliest epochs of cosmic history. In other words, the galaxies of the void are living fossils, snapshots of what galaxies looked like billions of years ago, preserved by isolation. A 2019 study in the Astrophysical Journal found that void galaxies have an average stellar mass roughly 5 times lower than similar galaxies in dense clusters, but their specific star formation rate, the rate per unit mass, is often higher. They form fewer stars overall, but they do so more efficiently and over a much longer duration. The cosmic void, it seems, filters out chaos. Even the shape of these galaxies tells a story. Without constant gravitational harassment, void galaxies are far more likely to remain pristine, disc-shaped, undistorted spirals rather than irregular remnants of collisions. The famous Galaxy Zoo project, where volunteers classify galaxies from SDSS images, has identified thousands of such elegant spirals drifting alone in the dark. As Dr. Karen Masters from the Galaxy Zoo team once said, "In the cosmic suburbs, galaxies live slow and quiet lives. They keep their shape." But the implications go deeper than morphology. The low density inside voids affects not only structure, but also the very physics of galaxy formation. In such regions, dark matter halos, the invisible scaffolding of galaxies, form more slowly and remain less massive. Simulations from the illustrious TNG project show that these halos have lower central densities and shallower gravitational wells, meaning gas cools less efficiently, which can initially delay the onset of star formation. Yet this slowness can be a long-term advantage. In dense regions, supernova explosions and active black holes often blow away gas, halting star formation for millions of years. In the void, where such destructive feedback is weaker, galaxies can hold on to their gas for longer, sustaining quiet. Continuous creation over billions of years, astronomers have even begun to wonder whether voids might offer uniquely stable conditions for life-bearing planets. Fewer nearby supernovae mean fewer deadly radiation bursts. Fewer galaxy mergers mean more orbital stability. Even the cosmic microwave background radiation, being slightly cooler inside voids due to the integrated Sachs-Wolf effect, contributes to a gentler thermal environment on a galactic scale. Of course, These are long-term effects playing out over hundreds of millions of years, but in a universe ruled by extremes, the idea that emptiness could nurture longevity is both scientifically sound and deeply fascinating. The local void adjacent to our Milky Way provides a nearby example. At about 150 million light-years across, it's a small hollow compared to the KBC void, yet its sparse galaxies show precisely these traits: low metallicity, steady star formation and undisturbed disks. They are cosmic hermits, still forming stars in their quiet corners of space. ESA's Herschel Space Observatory confirmed this trend by observing coal dust in these galaxies, suggesting minimal pollution from earlier generations of massive stars. It is as if these galaxies never experienced the violent urbanization of clusters, the harsh radiation, the supernova winds, the gravitational harassment. Instead, they exist in near-perfect balance, isolated yet stable. Some cosmologists even propose that studying these pristine void galaxies could help calibrate the true rate of star formation in the early universe. Because their environments are so pristine, they act as natural laboratories for testing how galaxies evolve without external influence. The JWST has already detected several distant analogues, small, gas-rich galaxies at high redshifts, forming stars in isolation. Their spectra match surprisingly well with the local void galaxies, suggesting that the physics of quiet star formation hasn't changed much in over 13 billion years. This continuity tells us something profound about cosmic structure. The voids are not empty failures of formation. They are controlled environments of stability. They slow evolution but preserve it. And the more we study them, the more we realize they shape the larger cosmic balance. By expanding faster, voids pull matter outward from dense regions, regulating how clusters grow and how filaments stretch. Their quiet interiors are counterweights to the gravitational chaos elsewhere, the soft rhythm beneath the cosmic storm. As NASA's cosmologist Joseph Silk once said, voids are the lungs of the universe. Through them it breathes. That breathing defines everything. The birth of galaxies, the motion of dark matter, the spread of light. Emptiness isn't absence. It's the condition that lets creation breathe. What if the force that built the universe, the one quietly driving its expansion, is also the one destined to erase everything we see? This ultimate question guides our final contemplative drift, the realization that the expansion of space, particularly the localized acceleration we experience within the KBC void, is leading the entire cosmos toward a state of profound, unending emptiness known as the final solitude. Astronomers call the mysterious pressure driving this fate dark energy, a force that makes up about 68% of the total energy density of the universe. Unlike gravity, which pulls matter together, dark energy pushes space itself apart. Today we live in a delicate, momentary balance. Gravity still holds galaxies, clusters, and our Laniakea supercluster together, but only locally. Beyond scales of roughly 1 billion light-years, dark energy dominates, stretching the cosmic fabric faster and faster. Measurements from NASA's WMAP and ESA's Planck missions show that this acceleration began about 5 billion years ago, around the time when dark energy overtook matter as the main driver of cosmic expansion. Since then, the speed of that expansion has continued to increase, an invisible, relentless tide, pulling galaxies farther apart each second. The current expansion rate, the Hubble constant, is about 70 kilometers per megaparsec. That means, for every 326 million light-years of distance, galaxies move away 70 kilometers faster each second. But in the distant future, this number will grow. If dark energy remains constant, as the L in the LCDM model suggests, the universe will expand exponentially forever. Galaxies not gravitationally bound to each other will drift beyond our reach, one by one, until even the nearest clusters fade into invisible distances. Already, galaxies more than 16 billion light-years away are receding faster than light due to the stretching of space itself. Their light will never reach us, not because it's too dim, but because the space between us grows faster than photons can cross it. In the far, profound future, this cosmic horizon will close even more tightly. Within roughly 100 billion years, every galaxy outside our local group, including Andromeda and Triangulum, will vanish from view. Astronomers describe this boundary as the cosmic event horizon, a limit beyond which light emitted today will never reach us, no matter how long we wait. It marks the final absolute edge of our observable reality. NASA notes simply that in the accelerating universe, the night sky grows lonelier. By that time, the Milky Way and Andromeda will have merged into a single, massive elliptical galaxy, often called Milkdromeda. Around it, the universe will be almost completely dark. No new galaxies will fall in. No light from outside will ever arrive. For the first time since the Big Bang, the cosmos will become a truly isolated island. In about 1 trillion years, even the faint glow of the cosmic microwave background, CMB, the afterglow of creation, will stretch to wavelengths longer than a meter, fading below detectability to any observers that might exist. Then, the universe will appear static and empty, its true origin hidden beyond their cosmic horizon. This scenario is called the cosmic dark era. It is not poetic speculation. It is a projection based on known physics. The continued outward push of dark energy confirms that the universe's ultimate future is one of quiet decay. The current leading theory for the ultimate fate of the cosmos is heat death. It doesn't require any exotic new physics, only the continuation of what we already see today, the steady acceleration of expansion driven by dark energy. Galaxies will drift apart until space between them doubles, triples, and then increases 1,000-fold. The distances will grow so immense that even gravity, the most persistent of forces, will lose its grip beyond local clusters. Simulations suggest that by the time the universe is 100 trillion years old, star formation will cease entirely. Gas will have been consumed or ejected, and the remaining stars, mostly long-lived red dwarfs, will slowly cool and fade. In this phase, known as the degenerate era, the universe will be populated mostly by cold remnants, white dwarfs, neutron stars, and black holes. Even those won't last forever. Over unimaginable time scales, black holes themselves will evaporate through Hawking radiation, releasing their mass as faint trickles of energy. The largest black holes will take around 10 to 100 years to vanish completely. After that, the universe will enter the dark era, a state of near-perfect emptiness. No stars, no galaxies, no heat, just thinly scattered particles and photons stretching toward infinity. As ESA describes it, the cosmos will fade not with a bang, but with an endless sigh of expansion. This is the ultimate triumph of dark energy. But there is a margin of uncertainty. What if dark energy changes over time? The hypothesis of quintessence suggests its strength could increase. If the expansion becomes so powerful that it overcomes even local gravity, tearing apart galaxies, stars, planets, and eventually atoms themselves, we enter the realm of the Big Rip scenario. For now, however, observations from Planck and the Dark Energy Survey suggest that dark energy is consistent with a cosmological constant, making the Big Rip unlikely, and a future of quiet decay the leading path. If the universe's future is one of quiet decay, then each galaxy cluster will become its own private universe, disconnected from all others by expanding voids. Astronomers in those future islands, if any exist, will have no way to infer the Big Bang. Their telescopes will reveal only static stars within a few million light-years, surrounded by black nothingness. The CMB will be gone. The cosmic web will be invisible. To them, it will seem as though their galaxy is all that ever was. Yet before that distant future arrives, we have billions of years, perhaps trillions, to measure, to explore, and to understand. Dark energy is not just the end of the story. It's the next frontier in cosmology, the final puzzle linking space, time, and quantum fields. What dark energy is doing isn't destruction. It's expansion without limit, a continuation of what began 13.8 billion years ago, a stretching of space that never stops. Issei calls it a universe accelerating towards solitude. In that solitude, physics reaches its simplest form. Expansion balanced by nothing. Energy diffused to uniformity. But today still belongs to light, to telescopes, and to the curiosity that refuses to fade. Because until dark energy wins completely, there's still time to look outward and learn. If this quiet journey has brought you even a small moment of peace, I'm deeply grateful you've spent it here with me. A gentle like or a soft tap on subscribe isn't just a click. It's a quiet encouragement that keeps these night stories alive. And if you'd like, I would love to know where you are listening from, for even those little glimpses of your world remind me that even across this vast distance, we still share one sky. May your night be calm, your thoughts clear, and your dreams filled with the quiet hum of distant galaxies still drifting through the dark. Good night, my fellow dreamers of the cosmos.